Hello, and welcome to this segment on biological nitrogen removal. I'm Ron Trigar. I'll be hosting this session with you all today, and I hope you enjoy it and it helps you with your operation of your treatment plants and also studying for exams. There's a lot to cover here, and we're going to get into all those different aspects of nitrogen and nitrogen removal. Now, remember that this is an abridged version, so it's a condensed version of what is a very intricate and lots of moving parts to the total biological nitrogen removal process. So we're covering some basics here. So if you ever want to get a little bit further into it and know a little bit more about it, we teach some classes here at UF Trio Center. There's other manuals out there. There's lots of stuff on the internet that has been printed, and a lot of training manuals have been built, and there's a lot of material out there. So you can definitely find it in just about a lot of your resources out there today. So we're going to kind of cover the basics of it. We're going to get into the different bacteria that are specialized that do this and their needs, and things that get those bacteria a little bit upset, maybe cause them to slow down a little bit, maybe inhibit them from operating properly, or maybe inhibit them from operating at all, which causes us plant operational problems. And we're also going to talk about operational problems that come from the nitrogen bacteria doing their job, as far as things like pH problems, chlorination problems, and alkalinity problems, some things like that, sludge that rises up in clarifiers and all that fun stuff. So we've got a lot to talk about, and I'm going to go ahead and get started into it. So I hope you enjoy it. So we have a copyright statement from the University of Florida Trio Center. It's the Trio Center stands for the Center for Training, Research, and Education for Environmental Occupations. And we appreciate if you want to reuse this or in some manner show this, that you get the written permission of the University of Florida Trio Center. Thank you for doing that. My name is, again, Ron Trigar. I'm a certified environmental trainer, and I work here at the University of Florida Trio Center as the senior training specialist for water and wastewater programs. And my contact number is 352-294-3881. And my email address is rtrygar@trio.ufl.edu. And we welcome you to check out our website at www.uftrio.org. You will find on the website, under student resources, as part of the water and wastewater programs page, you'll find manuals there that we've posted, and a lot of different student resources for the wastewater and water treatment side of the operations. We have formula sheets and a lot of tutorials there, and you can download a copy of a manual we wrote many years ago called Nitrogen Control in Wastewater Treatment Plants. This was the second edition that we wrote, and the first edition that we printed was actually for the Department of Environmental Protection Operator Certification Program here in Florida, as a supplemental guide to C-level operators, or operators that were taking their C license, as a supplement to the coursework that was necessary for them to take the test, because there were questions on our exams about pop-ups and nitrification and denitrification, but the manuals didn't really get into that very much. The required course reading that we had at the time didn't really get into it too much. So we wrote a supplemental manual, and the manual that you see now, rather, is this is the second edition. So you can get this from us here at the University of Florida Trio Center. You can find it online and at our website. So go check that out. And much of the material that I'm going to present to you comes from that research that I did to write that manual. So looking forward to sharing this with you guys. Some important references. I just want to point out that much of the material that we will show here and that I've learned over the years came from the California State University out of Sacramento, the Operation of Wastewater Treatment Plants, which is Volume 1, Volume 2, and also the Advanced Waste Treatment Manual that is currently in print. And I believe there's some changes coming here shortly from California State University, but these are the courses that are necessary to take the C. This is the Florida C license exam, and then if you're taking the B license currently, you'd have to have the additional course, which is the Advanced Waste Treatment. So much of the material that I'm going to be talking to you about will come from there, and also from courses that we've presented here in the past and my manual on nitrogen removal. Another great reference that you'll find is from the EPA, and a lot of these manuals are free as well. And you can download these either from our website, or I can send them to you. You can get them from the EPA website if you just go to epa.gov, and in a search window, just type in EPA manuals of operation, and you'll find a whole bunch of EPA documents that are free, and you can download those yourself as PDF files. So there's activated sludge, biological nitrogen removal, disinfection, troubleshooting guides that we're going to be talking about in this session, and those come from the EPA, and I'll be sharing those with you. So the first question on the table right now is, first thing into our class, is why do we remove nitrogen? What's the big deal? Why is nitrogen being picked on so much as a nutrient? Well, maybe many people don't realize what the effects are of nitrogen. So that's why we're here, and that's what we're going to be talking about. So why do we remove nitrogen? What is the issue with it in wastewater? Well, in wastewater, especially where we discharge the wastewater, the nitrogen represents itself as a nutrient, and the nutrient is to aquatic plants that we call algae. And so we're trying to reduce the effects or the negative effects of the algal growths in the water bodies. And sometimes algae blooms occur, and we have a large growth of algae. And when the algae succumbs and starts to decay, bacteria then come to work and start to actually decompose the algae, which places a large oxygen demand on the water. You guys probably recognize out there that algae also can be toxic to humans, and some algae can be toxic to humans and fish. And so we want to protect the water bodies from that, and also our health. Nitrate is a problem in drinking water. So there's a lot of different reasons why we would have to control or somewhat limit the effects of nitrogen in the aquatic environment. So first question, or first answer, is that we know that ammonia, nitrate, and nitrite in their various forms can be toxic, depending on what form these are in and where they are. If it's a gas and we're breathing it, or if it's in the drinking water and we're drinking it. We also know that ammonia in the environment exerts an oxygen demand from the bacteria that are willing and able to use the ammonia as an energy source. So there will be an oxygen demand placed on the environment as the autotrophic bacteria start to use this ammonia as an energy source. We know also that ammonia and nitrate stimulate the growth of algae and other aquatic plants. So it's a nutrient, plant available nutrient, and we want to try to limit the effects or the negative effects of the eutrophication of the water body where the nitrogen is being discharged. And we also know that nitrates, nitrite, ammonia in their various forms can definitely cause us plant operational problems. So we want to talk a little bit about what causes some of these plant problems, these treatment plant problems, rather, that we experience in our day-to-day operations. And this happens in these problems can happen in many facilities. So we want to try to uncover some of those mysteries on why we have chlorination problems or effluent toxicity problems. So plant operational problems can result from forms of nitrogen found in the wastewater coming into the treatment plant, or being found through different places of our treatment plant, like in our clarifiers or aeration tanks or chlorine contact basins, those types of things. And we can definitely see that various forms of nitrogen can cause problems in clarifiers, especially as nitrogen gas. And nitrogen gas can get trapped into the flock or into the sludge that is settling in the clarifier, and put an N2 there for nitrogen gas. And as nitrogen gas tries to escape to the atmosphere and rise to the surface, sometimes it carries sludge particles with it and causes what we call pop-ups. And sometimes it's from a denitrification down inside the clarifier, and the actual bacteria producing nitrogen gas from nitrate. we know that sometimes the whole sludge blanket can rise up. So it's not just little pop-ups or little pieces of ash that come to the surface. Sometimes the blanket can come up, and sometimes the blanket can rise in a settleometer. Sometimes your actual settleometer rises within a few hours, and you wonder why that happened. So we want to take a few minutes to talk about that as we go through this class. So again, nitrogen gas rising to the surface can cause rising sludge blankets and clarifiers and pop-ups. We know that high amounts of ammonia and organic nitrogen that enter treatment plants can cause an oxygen demand on the actual bacteria or the oxygen we're supplying to the bacteria. So the demand on oxygen comes from these bacteria using oxygen while they oxidize carbon from carbonate into energy for the bacteria to grow, and they're going to use the ammonia as an energy source. So they place a demand on oxygen on our treatment plant. So it's tough to maintain dissolved oxygen at certain times of the day because of things like high TKN in the influent. Now, TKN, just to give you a little bit of a heads up, TKN is made up of several things, which we generally say organic N, which is organic nitrogen, and ammonia, and we're going to put NH3 here for ammonia, and we're going to say that those are the two things that make up what we call TKN, and I'll talk about that a little bit later. So if we have a high demand on oxygen in our aeration tanks because of a high amount of TKN or organic nitrogen and ammonia coming into the treatment plant, then we can obviously have problems downstream of the aeration tank. If it's tough to maintain DO in the plant, then we may not actually do all the treatment that we're hoping to do in the actual treatment facility. So we could have cloudy effluent leaving in the through the clarifiers and out into the effluent from high effluent TKN. So we would measure the TKN going out and find that we still have some ammonia or organic nitrogen left in the effluent, and it's flowing out into the environment. So could cause some effluent cloudiness or turbidity issues. Then if we have problems with, say, things like untreated waste, not fully oxidized ammonia and things like that all the way through the plant, then we could actually have something called an intermediate form of oxidized nitrogen. And an intermediate form of oxidized nitrogen is found right here, which is called NO2, which is nitrate, or I'm sorry, nitrite. Nitrite with an I is the form of nitrogen that we really want to pay attention to with respect to chlorine demand. So if we have a high chlorine demand and we have nitrite in the effluent, then it stands to reason that we could have poor fecal coliform kills. And if we're not chlorinating properly, or chlorine's being used up to force nitrite to become nitrate, then we end up with a potential for poor fecal coliform kills because we can't keep a chlorine residual. And then lastly, we find that if we have problems with ammonia and nitrite leaving the treatment plant, we could certainly have effluent toxicity. So effluent toxicity, or what we sometimes refer to as a bioassay test, bioassay is also known as a whole effluent toxicity test. That's when we take some of our effluent water and see how many organisms can grow in it. We put some crustaceans and things like that in the water in different dilutions. And we try to see, hey, so how many of these organisms will continue to survive? How many of them will grow in size? How many of them will reproduce? There's different mortality rates. And if we're failing effluent toxicity tests, sometimes the issue comes back to high amounts of effluent ammonia or even TKN in the effluent. So unfinished nitrogen species or incomplete nitrification can in some cases cause that. So that's a pretty big list. It's a pretty big list of plant operational problems that we could find from inside the treatment plant from different forms of nitrogen. So nitrogen removal, biological nitrogen removal, is a system or a process that requires several groups of bacteria to all work together. When we say groups of bacteria, we're saying like a whole lot of different genus of organisms, of bacteria that will work together to oxidized forms of nitrogen we call ammonia or ammonium, and convert that into nitrite, and then another group of bacteria come along and convert that into the nitrite into nitrate, and then we have what we call an oxidized form of nitrogen. So we rely on these bacteria to work together. We also rely on other groups of bacteria to convert the now formed nitrate into forms of nitrogen gas, but we kind of like to have that happen in other parts of the treatment plant, not near the effluent part of the plant. We'd rather have that nitrogen gas conversion in a controlled environment, maybe in what we call an anoxic tank. So when we have an anoxic tank working properly and we're getting the conversion of nitrate to nitrite to nitrous oxide and then finally to nitrogen gas, we actually release the nitrogen in a controlled environment back to the atmosphere, and we produce a little bit of what's known as alkalinity. So you're going to hear me say alkalinity a lot in this session, and I really hope that it gets kind of, ingrained in your mind that how important alkalinity in the form of bicarbonate is to this process. And many operators tend to forget that that is such a necessary component, and we don't measure we don't measure the alkalinity coming into the treatment plant, or we don't measure it through the process, and it becomes one of these types of lab tests that we tend to forget that how important it is. I want to try and stress that in this video segment to you guys, that it's important for operation of the whole treatment plant to maintain correct pH, and also to make sure that we're going to have the right components there for the bacteria all the way through the process. So it's a huge part of this. When one group of the bacteria slows or stops or is inhibited, we can have process problems. So for instance, if one group of the nitrifying bacteria, we call them Nitrobacter, if those bacteria tend to be inhibited or don't show up for work that particular day, then we could actually have problems with nitrite leaving the treatment plant and causing chlorine demand problems. So we're going to have to pay attention to this whole biological process, this whole biochemical process, to make sure that we treat the wastewater properly and we have a stable effluent and a good efficient process all the way through. So what we want to talk about now is the forms of nitrogen that we find in wastewater. So we're going to be talking about all these different forms today, and I want to make sure that we have the somewhat of a comprehension of what these forms are and where they come from. So I apologize now ahead of time if it seems a little graphic in some cases, because wastewater treatment is wastewater treatment and humans produce waste. And so when we start talking about where nitrogen comes from, we're pretty much starting with our effluent of our body into a toilet and then moving on from there. So be ready for that, because it is the nature of the beast. So let's go ahead and dive into this. So we see all of our lists here. We have a pretty substantial amount of nitrogen species in wastewater and different places in our treatment plant. We have what we call organic nitrogen, which essentially comes from the human body. Just imagine, if you will, the urine or urea that we excrete from our body is carrying with it forms of nitrogen that our body did not use or was converted in our body, and that was produced or kind of cleaned out of our blood from our kidneys, and our bladder stores it for a while, and then we excrete nitrogen in the form of organic nitrogen into essentially a toilet. We'll say, because we're talking about wastewater treatment, we're going to send it to a wastewater treatment plant. So we're going to insert this into the collection system, either at our residences or homes or commercial establishments, or University of Florida Trio Center restrooms, or whatever, wherever you are. And that's kind of what we're doing. So you can kind of see the organic nitrogen is made up of several different elements. We have carbon, we have 4 hydrogens, we have 2 nitrogens, and we have an oxygen here. So that's essentially the ingredients, we'll say, of the organic nitrogen component. Next on the list is ammonia and ammonium. Now, ammonia is very common term for us in the industry. We generally say that ammonia is coming into the plant from humans, and that's true in a lot of ways, but I do want to stress that ammonia and ammonium exist together, and there's what we call an equilibrium of these two compounds, and we want to make sure that we understand where and how these two change a little bit in the process. So we're going to be covering ammonia and ammonium quite in depth here this session. I do want to also point out that the ammonium has a little plus here next to it, and the nitrate, these are ions, by the way. So when I put the little negative charge next to it or a positive charge, that means it's an ionized form of nitrogen. So we have nitrate and nitrite next on the list. You see that we have nitrate as NO3 and nitrite as NO2, and again, they are sort of negatively charged ions. And then next on the list down near the bottom, we have nitrous oxide and then nitrogen gas as N2. So we will be talking today about oxidation of the organic nitrogen into ammonia and how ammonium and ammonia exist together. We'll be talking about how bacteria convert the ammonia or ammonium into nitrite and then nitrate. And then another group or another classification of bacteria that we're going to call facultative heterotrophic bacteria convert the nitrate back to into nitrogen gas for us. So back to the atmosphere it goes, into the air that we're breathing right now. A certain percentage of nitrogen gas in each cubic foot of air that we're breathing right now. Depending on where you are, that ratio or that percentage can be higher or lower than in other places, but generally the nitrogen gas is going back to the atmosphere. So what are the steps in the nitrogen removal? What do we need to remove nitrogen or convert it? Let's talk about converting it instead of saying we're removing it. We are kind of removing it from the wastewater, obviously, but we're doing more of a conversion all the way through. We're kind of changing this back into a form that's going to be an atmospheric gas and like I said earlier, just re-enter the atmosphere. So we're going to have 3 steps to talk about here today. We're going to cover the first step called ammonification. We're going to be talking about nitrification, which is an essential part of the operation of the facility. And then we're going to talk about denitrification, which is the conversion of the nitrate into nitrogen gas, back into the atmosphere. So we've got 3 things to cover here today. The first step, ammonification, is a somewhat forgotten step because it just happens. And as operators go, we're not really seeing too much of it. We're not doing too much to control it, I would say. But I do think that you all need to know what it is because it does affect our treatment process all the way through on what gets ammonified and what doesn't get ammonified and then has to be worked on or converted in the treatment process. So it's an important step that I think we tend to forget about. So we're going to start off our discussion. I have a rectangular shaped nitrogen cycle here. Obviously in some cases you can see this be shaped as a round cycle or circular shape, where we have the nitrogen cycle. I tend to like this one because it kind of sets it up a little bit easier for me to display and show you what I want to show you here. So the first thing I want to say is that with ammonification, the word ammonification is at the top here. Ammonification by microorganisms happens in the collection system for the most part, all the way through from the point of entry into the collection system, all the way through to the headworks of the treatment plant. So the organic compounds are the urea and the urine that we talked about. I'm going to put urea here, and we're going to talk about that because there is a part of that is nitrogen. So we call organic nitrogen the beginning of the phase. This is coming from the human body, and we're going to discharge the urea into a collection system. So from our body into essentially a toilet with some water to flow the urine and the waste product down through the pipes into the collection system, into the treatment plant. We're going to be mixing this with potable water that is used for flushing the toilet. So the potable water has things like oxygen in it, carbon dioxide or carbonic acid from the atmosphere. We're going to have chlorine, from the actual tap water. Potable water may have chlorine in it from your municipal water supply. We're going to have hardness in there. There's going to be calcium hardness and sometimes magnesium hardness. We're going to have alkalinity present. We'll possibly have fluoride present and corrosion control chemicals that water operators put into the water distribution system to prevent corrosion. So just think about that. I mean, the water that we use to flush the toilet already has a lot of components in it. It has dissolved oxygen and certain pH and temperature as well. So that is going to start this process for us. That is actually the start of this chemical reaction and chemical change. So from the toilet and moving through the laterals into the trunk lines and the main lines of your sewer system down into the force mains or lift stations, then into the force mains and on its way to the plant. It gets well mixed and enters the wastewater plant as a homogeneous blend that we generally call sewage. So the first line, the first red line that you see here is the organic compounds flowing through the wastewater collection system and making their way to what we call the headworks of the treatment plant. So coming up into the headworks of the treatment plant, we have had something called ammonification happening. So ammonification converts the organic compounds into ammonia, but remember, it's not all going to be done. We're still going to have some organic, I'm going to put ORGs for organic, and we're still going to have some organic nitrogen entering the treatment plant. Now, depending on the time in the collection system and the temperature and the amount of activity of the microorganisms, you may have more organic nitrogen than in other in other places. You may find that you have a lot of organic nitrogen coming in the plant in some cases, and in other cases you find you have very little. It just depends on the distance of the collection system, the length of time, any kind of bacteria action that occur in there, and where these chemicals are making their entry point. If you have a subdivision that's very, very close to your wastewater treatment plant and a lot of homeowners there that flush the toilet to get ready for work in the morning. So you may have a large influx of organic nitrogen coming into the treatment plant early in the morning because we have a lot of flow coming in early in the morning and it's in close proximity to the wastewater plant. So that organic nitrogen will also need to be converted or will be converted into ammonia inside the wastewater treatment plant. So I want to keep bringing this up to you all to recognize that we don't just have ammonia coming into the treatment plant, we have ammonia and organic nitrogen. And that will end up being ammonified in the aeration tanks and potentially in your primary clarifiers if you have those. And that increases the load of the ammonia coming into the aeration tanks. So it's a forgotten form of nitrogen that I want to bring up to you that you want to pay attention to. So remember, this is not just a discussion to help you, sit for an exam or study nitrogen removal for exam purposes. This is operational 101 stuff here. All right, so we have our organic nitrogen being converted into ammonia. So ammonification happens here. So we're entering the collection system at the treatment plant, or rather into the treatment plant from the collection system. So it's a process that happens usually pretty naturally in the collection system, as long as the wastewater is flowing through the pump stations and the lift stations and into the headworks of the plant. We're having this occur. It just depends again on how far the distance is and the time. You can kind of see where it says it's the conversion of organic nitrogen into ammonia by decomposition and hydrolysis. The mixture of the water and all those elements in the water causing hydrolysis of the organic nitrogen into ammonia. So I do want to point out here that ammonification is the conversion of organic nitrogen into ammonia, which you guys probably recognize ammonia as NH3. But don't forget that we also have something known as NH4, and this is an ion, and we also have that coming into the treatment plant. So it just depends on the pH and the temperature on how much of either one of these we have. I'll discuss this a little bit more here in just a minute. Okay, so coming into the treatment plant, we have the ammonia and ammonium that has been converted in the collection system. And now the first step that we're going to talk about once we get into the treatment plant itself is called nitrification. So we are going to convert the ammonia and ammonium into nitrate as a final product. And you can kind of see here in this picture, I'm showing you an aeration tank. This is at a small package type treatment plant that uses round precast concrete tanks as their aeration tanks with a single diffuser header or airline coming into the aeration tank. And this would be carrying oxygen with it. We know that air has about 21% by volume of oxygen. So we're pumping some air into this tank that has oxygen and other gases like carbon dioxide and nitrogen, but the oxygen is being used by the bacteria in this aeration basin to convert ammonia into nitrate. So we're going to talk about the ammonification a little bit more here in just a minute, but this is what's happening in the aeration system with the red line showing. So we had the ammonia or ammonium coming into the plant, and it's being converted to nitrite and then nitrate. And you can kind of see the red lines on here, the red arrows on here, kind of showing you the pathway. So that's going to be our steps. That's going to be the two-step process that we're going to be talking about here. But I want to go back and just describe one more thing to you guys a little bit more in depth. And I don't want to forsake or forget that we have something kind of occurring behind the scenes. And I mentioned this already, that we have ammonia and ammonium. I went backwards a slide or two here. Let's talk a little bit more about this ammonia and ammonium. So in the wastewater treatment process, in the collection system, we have this thing called decomposition by bacteria, and we have hydrolysis occurring. This is actually what's playing a part in the difference between the ammonia and ammonium coming in the plant. So at a pH, an influent wastewater pH, say, let me go ahead and erase some of this stuff off of this slide and give myself a little bit more room. And let's go back to this. So at a pH of, say, let's say we have a pH between 7.0 and 8.0. Okay, so a pH between 7 and 8 in this range. You want to say pH range here. Okay, so at an influent wastewater pH between 7 and 8, we're going to have a compound known as ammonium, and it's NH4 plus, is going to be a greater concentration rather than ammonia. So this is occurring because the pH and the temperature of the collection system either speeds up or slows down the rate of the conversion of the ammonia and ammonium, or from the organic nitrogen. So with higher pHs, we tend to find more ammonia as a dissolved gas. I'm going to put over here, ammonia can be found in the wastewater as a dissolved gas, like ammonia gas, and you can smell it. The form called ammonium, I'm going to write here ammonium. Ammonium is an ion. It's ionized. It's an ionized form of nitrogen. You can see that it has a plus symbol here. So it's an ionized form. It's an ion that's in the water as a part of the water column. So ammonium is ionized and ammonia is unionized. Notice that the ammonia has no negative or positive symbol next to it. So it's unionized. In nature, in our wastewater treatment plant collection system coming into the plant, we have dissolved ammonia gas. Now it depends on the pH. As the pH is around 7 to around 8, we're going to have a higher percentage of the ammonium. We're going to find that we have somewhere around between 100% and somewhere maybe to, let's say, 85% as the ammonium. And then over here, we're going to have somewhere between 0% and say maybe 15% of ammonia coming in the plant when our pH is somewhere between 7 and 8 in the influent wastewater. How this actually changes and how this can be affected is if we raise the pH up, or if the pH goes up for some reason. Maybe we added some chemicals to stop odors, things like that. And as the pH gets up over 8, closer to 9 and 10, the pH increasing will cause the ammonia gas to be a little bit higher. The concentrations will shift, and we'll start to see higher amounts of ammonia as a dissolved gas rather than ammonium. So it's called an equilibrium shift. They actually exist together in the wastewater, but the percentages will shift. Depends on the pH and temperature and other mitigating factors, but these are the two main things. So I just want to make sure we're clear on one thing here, that even though we say ammonia coming into the plant, and I will probably still say ammonia from time to time, I do want to kind of point out that really at a pH of 7 to 8.0 in your influent wastewater, it's mostly in the form of ammonium. And the ammonium is going to be, let's say, less toxic as a nitrogen form to aquatic organisms than the ammonia will be. So ammonia tends to be somewhat toxic to aquatic life, and some of the crustaceans and fish and things like that. Any of you raising fish in an aquarium probably know that an increase of ammonia will cause a fish kill, and because that's a dissolved gas, it's passing through the gills of the fish and into their bloodstream, so it's causing the mortality. So ammonium as something that's in the water that's not going to be a dissolved gas is less toxic to the aquatic organisms. So we just want to make sure we're clear on that. And this changes, this amount changes due to the time in the collection system. So again, just want to kind of point that out to y'all and make sure we're clear. All right, so let's go back to our slide here. So nitrification, we said, was the ammonium coming into the treatment plant that's being converted into nitrate. Why do we always say ammonia? Why is it that ammonia is the word that we use? One of the things that I have found over the years is that when we measure for this in a laboratory or measure it in our treatment plant process labs, our small plant labs, we generally have test kits that say that we're testing for ammonia, and it's the easier form of nitrogen to be tested for with reagents, things like the Nestler's reagent and some of the other chemicals that we can use as reagents to be added to a sample and cause a color change that we could measure with a colorimeter. So the ammonia becomes the form that's easier to measure rather than the ammonium. In fact, if you wanted to know how much of ammonia was present and how much ammonium was present, we would have to run an ammonia test. But at the time of collecting the sample, we would also have to collect something known as the temperature of the liquid at the time of sampling, and the pH at the time of sampling is important. You could measure dissolved oxygen as well, which is also a component that's measured in the field as a field parameter. But there's a conversion table or conversion tables that use the temperature and the pH to help us convert or give us a measurement number of how much ammonium is really present based on the ammonia value that we ran with our laboratory equipment, and then converting it into the ammonium proportions based on what the temperature was at the time of sampling and what the pH is at the time of sampling. So those two things have to be done in the field because those will change rapidly and must be done within 15 minutes of sample collection. Even dissolved oxygen is something that is better measured in situ, or what we call in situation, in the actual liquid itself. So the ammonium that we pointed out here is a common term. We say it's the conversion of ammonia, but I do kind of think it's important that we recognize that it's at a certain pH value, say a 7.0 to 8.0, it's usually in the form of ammonium, which is NH4+. Okay, so we'll talk about that as we go through. All right, so we're going to convert this stuff into nitrate. Nitrate is NO3, a little negative. All right, so let's jump into this. So here's our nitrogen cycle again. We kind of took a little sidestep there to cover that base material before this, but let's get back to this slide now. So we came in the treatment plant with at our headworks, and let me go ahead and erase this slide because or that little thing there, because I want to kind of put up here. Remember, it's not just NH3; it's also this. Okay, so NH4 plus. So it's both of those coming in the treatment plant. The ratio is somewhere, around, 70% ammonium and around 30 something percent ammonia. Sometimes it's even less than that. So we have this ammonium and ammonia coming in. Plus, we also have some organic nitrogen that's also coming into the treatment plant. Remember, this organic nitrogen is here, organic N here, coming into the plant. And so some of that organic nitrogen is converted, some of it's not. So we have somewhere between 70% ammonium and 30% organic N and 70% ammonium. All right, so we're coming in the treatment plant. This word, nitrification, takes place. This is step number 1, and this is step number 2 at the bottom of the chart. So we go from ammonium to nitrite and then to nitrate. And that's the 2-step process. This is called an oxidation process. So this is oxidation, and this is oxidation over here. So with the word oxidation, I hope that you're putting in your mind that this includes something known as oxygen, or that we have to have oxygen present for these bacteria to do their job. All right, so let's move on. The 2 steps that are involved with nitrification. Again, just to kind of keep it basic here, and remember what I said a little earlier, this is just a basic tutorial on what the processes are. This is not going super in depth on how much ammonium is being converted with how many moles of oxygen. I'm not going to try to put any kind of stoichiometric equations here. We're not going to balance equations. So I just want you to know that this is the steps that are occurring. So if you're taking an exam, this will help you. If you just want to know a little bit more about how this stuff affects your treatment plant, this will help you. So our slide says ammonium. I keep wanting to put in here that we also have ammonium present, and we have oxygen. This is known as O2. And we have certain amounts of oxygen with ammonia in the presence of Nitrosomonas group. This is a bacteria species or genus name, and there's a lot of different subspecies of Nitrosomonas. But Nitrosomonas is the first group name that we have of bacteria, and this will yield or produce for us a equation that shows nitrite. We'll have some nitrous acid, HNO2, nitrous acid, and we'll have some more Nitrosomonas being formed. So we'll have more bacteria is being produced. All right, or are being produced. If everything's happy and everything's working good, we'll have some of that. Now, remember, there's other things happening with respect to, say, alkalinity being consumed, because these bacteria will use alkalinity to as their carbon source. So they will take some of our alkalinity away from us, and they will produce acid. So we're going to find that the pH value of the wastewater or the pH of the mixed liquor will start to drop as we start to nitrify. So this is step number 1, and then we have step number 2 occurring. Let's kind of draw an arrow here and say, let's go this way. All right, so we had nitrite, and we have more oxygen being added. This is O2, and we start this process this way. And we have another group of bacteria here called Nitrobacter. That's a genus name. Again, remember, there's several subspecies of Nitrobacter also here, but there's a lot of these bacteria present in our mixed liquor that will do this form of oxidation of nitrogen for us into a product called nitrate. And we have NO3. We'll put a little negative there because that's an ion, and we end up with more Nitrobacter. So if everything's working properly, we go from ammonium to nitrite to nitrate. And the little statement at the bottom here is a way for you to remember it. This is one of my students in the classes many years ago said this is how he remembered it, and kind of coined this phrase: ammonia at the right rate And we always start off the process with ammonia because it starts with the letter A. So ammonia starts it, and then we have nitrite and then nitrate, ammonia at the right rate. So it's NH3, NO2, and NO3. So ammonia at the right rate. Okay, so what affects nitrification? So that's a two-step process that occurs very quickly in a treatment plant, given that all of the environmental conditions would be best. If the environmental conditions aren't exactly right, or there are some problems, maybe we don't have enough alkalinity, we don't have enough food for these guys, not enough oxygen, the temperature's too cold, we have too short of a detention time, all those factors go into limiting the amount of nitrification that we could have. So nitrification is reliant on a lot of different external conditions to be just right. The temperature, the process temperature, this is the MLSS temperature. The MLSS temperature can't be too cold or too hot. They say that that we should not be below, say, 15 degrees Celsius. Might be too cold for efficient nitrification. So say like less than 15 degrees C. Now it will work at other temperatures lower than this. It just takes longer and more bacteria to make this work. And then if we end up with temperature say above, I think it's somewhere around 40 degrees C, we end up destroying some of these bacteria as well. So we don't want the wastewater temperature to be too hot, obviously. And that's not usually the problem unless you're an industrial plant. The problem that we generally see is right here, is when the temperature drops in the winter time. Now here in Florida, we don't get temperatures that drop too low as say compared to say Madison, Wisconsin, or in Minnesota, but we definitely do get some colder temperatures here in the winter time, and our mixed liquor temperatures tend to fluctuate. So our mixed liquor temperatures in Florida can say go from somewhere around 15 degrees Celsius up to 25 degrees Celsius, maybe even higher down closer to the south part of Florida into the Florida Keys. We might start seeing mixed liquor temperatures that stay pretty constant, let's say above 25 degrees Celsius. So we don't see as much temperature problems in those areas with nitrification as we do, say, in this part of Florida where I'm at, in the north central Florida area. In fact, we had frost all over our vehicles this morning, and it's March 8th, and we had a good layer of frost all over everything when I got out to work this morning. The concentration of ammonia can actually be a problem. We can have too much ammonia coming into the plant. Now, slugs of ammonia are generally a problem. If the ammonia is constantly high, bacteria will acclimate to this. There are a lot of different species. But if we have slugs of ammonia that come in that are too high from time to time, that can be a problem. We can have slugs of ammonia come into our treatment plant from side streams that we have within our own plant. Let's say if we have anaerobic digesters and we supernate our digester, we could actually slug load ammonia back through the plant. So the concentration of ammonia can't be too high, and it shouldn't be in slugs coming in. When I say too high, I mean somewhere close to say 100 milligrams per liter or higher. Different compounds like landfill leachates, anaerobic digester supernate, and those types of fluids can cause slug loads of ammonia coming into the plant. You could even find high slug loads of ammonium coming in the plant during certain times of the year or events that you might have planned in your community. We have football stadiums that break for halftime, and we have a lot of flow come into the treatment plants during halftime. Some of the university wastewater treatment plants, like here at the University of Florida treatment plant, they tend to get a high amount of flow during halftime, and it may carry with it a lot more ammonia than at the other times of the week when there's no football games in session. So the dissolved oxygen could be driven down because of the excessive amount of ammonia coming in and the burden that places on the available oxygen in the mixed liquor. So we call that dissolved oxygen. So if the dissolved oxygen drops too low, or it's already too low, we may not have enough oxygen present for the bacteria to do their job. We know that it takes, let's just put a couple numbers up here. We know that it takes about 1.5 pounds, and I'm going to put pounds of DO of oxygen to convert 1 pound of BOD. We know that that's a common ratio. But how much extra oxygen does it take to convert ammonium into nitrate? Well, it takes, for that process, it takes about 4.6 additional pounds of O2 to convert 1 pound of ammonium into nitrate. So that's a pretty large oxygen demand placed on the aeration system from the amount of ammonium coming into the treatment plant. So to meet all of the removal or the conversion of the BOD to be used up by the bacteria for food, and also to convert ammonia to nitrate, we're going to need somewhere around 6.1 pounds of total oxygen to do those jobs. And it takes a lot of aeration capacity to fulfill this requirement. That's why the aeration tanks are generally much bigger in BNR, or biological nitrogen removal plants, and the capacity to put the air in there is generally much higher as far as horsepower of the mechanical aerators or the horsepower of the blowers. And the efficiency of the diffusers is important in this case. We usually have to have good, efficient transfer of oxygen into the mixed liquor. So here we see in red, this is an important component. Obviously, all this is important, but here's something that we want to pay a specific attention to. The process pH, the influent pH as well, but the process pH is important. Bacteria, especially these nitrifying bacteria, tend to be very sensitive, and the sensitivity causes us to see the process fail with respect to, say, we're not making nitrate or we're not making nitrite, and we're having chlorine issues, and we're having some problems with ammonia leaving the plant because the process seems to be, not working properly. So the pH needs to be monitored. Influent pH coming in should be somewhere in the alkali phase, somewhere in the upper sevens, let's say, somewhere definitely above 6.5. So if our pH is above 7, we're usually in pretty good shape. So a pH of 7.2 to 7.8, we're usually pretty good shape. It's when the nitrification occurs inside the plant that the pH may fall because of the nitrous acids that are formed. So we could end up with some acidification, especially if they're using up the carbonate from the carbonate alkalinity, and then we end up with a very low pH. So the process pH could drop. So we generally don't want it to be, let's say that we don't want the process pH to be less than 6.5. And we certainly wouldn't want it to be, say, greater than, let's say, 9.5. We wouldn't want it to be too high over here, because then it's too alkali and it could cause problems that way. But generally, the lower pH is the problem. So it's when the bacteria kick into high gear and we end up with a lot of dissolved oxygen and bacteria able to nitrify for us that we end up with the pH dropping. Where most plants see this, or where a lot of facilities see this problem, is in their aerobic digesters. We tend to waste activated sludge into these aerobic digesters, and then we end up with nitrification taking place because the DO goes way up in there, and then we end up with acids being formed, which drives the pH of the aerobic digester mixed liquor or the solids down, stay close to 6 in some cases, or even lower. So that's an important component. The next one is extremely important as well, because the alkalinity provides a carbonate source or carbon source to these nitrifying bacteria. So nitrifying bacteria are a specialized group of bacteria that we call autotrophs. An autotrophic bacteria can make its own energy from a chemical source. So a chemical source in this case would be ammonia or ammonium, and they make the energy from that, but also they consume carbon from the carbonate alkalinity coming in, or bicarbonate alkalinity. So they're their diets are a little specialized as compared to, say, some other bacteria. So autotrophic bacteria have a little bit more specialized diet and a little bit more needs for some specialized forms of carbon and energy. So they get that from the ammonia and the bicarbonate alkalinity. So if we don't have enough alkalinity coming in the treatment plant, we are definitely going to have some problems. So we have to have enough alkalinity coming in. And when we say not enough, we mean somewhere that we're less than, how about we say for this example, let's put less than 200 milligrams per liter, as CaCO3, and that's how alkalinity is expressed. If we're too low, then we may have a problem, especially if we have a lot of ammonia coming in that has to be converted into nitrate. So we want to make sure we have enough alkalinity matched up. And by the way, we always want to have some alkalinity left at the end of the process so that we don't have pH problems downstream, especially if we're using gas chlorine as our disinfectant. We certainly don't want to have a pH drop because we're adding an acid to the water, and then if there's no alkalinity there, the pH will drop. The retention time in the aeration tank is extremely important. We have to have what we call oxic sludge retention time. And if it's too short, we won't have enough time for the bacteria to actually complete nitrification. So we need several hours of detention time. So I'm just going to put up here hours of DT, which stands for detention time. We need several hours for these bacteria to do their job. That's why, again, think about the aeration tanks and how big they are in these processes. The aeration tanks are built big specifically because there's a limited amount of nitrifiers and we need the maximum amount of time for them to do this job. Where we generally find problems downstream in some of our plant processes is when our detention times drop too much or too low, and we don't get enough time for the bacteria to do the complete nitrification in the peak loads of the day coming into the plant. So that's why usually aeration tanks are oversized for that purpose, to make sure that we completely nitrify. If we don't have enough capacity or aeration tanks online and our flow spikes during certain times of the day, especially if it's carrying a lot of ammonium with it, then we're going to have some issues downstream with incomplete nitrification. And we'll talk about that in a little bit. Where this says F to M ratio being too high, which generally represents we'll call this an organically overloaded treatment plant, means we just don't have enough mixed liquor volatile suspended solids. The MLVSS is too low. So we don't have enough bacteria to do the job. So if the MLVSS is too low and the FM is too high, the FM ratio is too high, we generally don't have enough bacteria present to do the job. Just want to point out that these aerobic autotrophic bacteria that we're relying on to do the work only make up somewhere between 5 to 10%, according to the recent research that we've seen. Somewhere between 5 to 10% are what we call the nitrifiers. And so if I say that nitrifiers, if I say that 5 to 10% of our MLSS or MLVSS, come on, Ron, it must be early in the morning. I'm kind of messing up my abbreviations here. So we have MLVSS. If only 5 to 10% of the MLVSS are nitrifiers, then we have a limited amount of these workers to do the job for us. So we need a little bit higher MLVSS amounts as far as pounds of solids inventory to make this work for us. So an F-M ratio that's too high also means it equals an MLVSS that's too low, and that's usually the milligrams per liter. And any toxicity, I love where it says toxicity too much. Well, of course, obviously toxicity is a bad thing, right? So think about what's considered toxic. Something that is toxic is something that is harmful to organs or organisms like us, or our organs, like we talk about poisons and things like that are detrimental. But toxicity means too much of really anything in the the wrong amounts. So you could consider oxygen to be toxic if the oxygen concentration is too high. We can consider water to be toxic if we drink too much of it. We can actually succumb to over doses of water. Who would have thought, just water could be toxic in the wrong amounts. So anything in the wrong amounts is generally considered to be toxic in some form. So toxicity it can be represented by a little bit of something or a lot of another thing. So we always have to pay attention to what's coming into the treatment plant, as far as pesticides, heavy metals, herbicides, bactericides. When we use chlorine in our treatment plant to kill filaments or to control a filament bulking problem, we're generally using a bactericide that is not just targeting the filament. It's also going to affect the nitrifiers. So toxicity can be found from external sources coming in the plant, but also from internal sources in the plant. And we have to pay attention to those things. Whenever we drain tanks, if we have empty basins or basins that have a lot of water in them or sludge that we are now going to return back to the head of the plant, when we drain those tanks back, we have to measure things like the pH, the alkalinity, the amount of nutrients that are in that. Did we have a reversion back to ammonia in that basin? Are we going to slug load our plant with ammonia, because we've held on to a basin for months and it's been sitting there getting fermented, and then we return that back to the plant? We could actually be causing toxicity in our treatment plants just from our own activities that we do. All right, so where do we get high ammonia loadings from? I just mentioned a little bit about wastewater treatment plants that serve like schools and things like that, but also pay attention to like DOT is Department of Transportation, and Department of Transportation along the United States highways run things called rest areas. And rest areas are places for humans to go and relieve themselves of the urine or the solid waste that we have in our bodies. So we want to do this in an environmentally appropriate fashion. So we stop at a rest area and we relieve ourselves. Well, the wastewater that's formed from these rest areas is usually really high in ammonium and ammonia, and that comes into a treatment plant, either there at the rest area or a municipal plant, in sometimes slug loads or higher loads than others. So if you think about a rest area that may be hooked onto your treatment plant, and during the course of a normal month, everything's fine, you don't see any problems. But what happens when we start traveling for the holidays, or to let's say football games, or for certain types of activities in your state? We have spring break and bike week and all that kind of stuff, where a lot of people travel to go to certain areas, and those rest areas that serve along the highways can see higher loadings during those times. So you can see spikes on organic nitrogen and ammonia coming into your plant because of the use of these rest areas. The schools, places like that, can have very high ammonia loadings. We're also finding many people now elect to use and build these facilities with low flow toilets or zero flow toilets, which means that the urine itself is what's moving the waste through the pipeline, and so it's becoming more concentrated. So the urine, the urea entering the treatment plant with the organic nitrogen is more concentrated than before. So we could see a definite load coming into the plant that places a high demand on our oxygen, our dissolved oxygen, and our aeration equipment. It says here that concentrations greater than 50 milligrams per liter can inhibit nitrifiers. Think about it as a slug load coming into the plant. So if we have a slug load concentration that instead of being, say, 40 milligrams of ammonia that normally comes in, we have a slug load now that's 90 milligrams. So slug loads that are out of the range of, say, 50 or so milligrams, that are outside or above the range, can be an inhibitory shock to the bacteria. Greater than 100 milligrams per liter in shocks can be fatal to a lot of the organisms, including the nitrifiers themselves. So we can actually see some problems in treatment plants from slug loads. Doesn't mean that the treatment plants won't be able to adapt and handle the waste, because some plants can handle high strength ammonia coming into the facility. It's when they come in slug loads that we see most of the problems. So slug loads can be an issue. Shock load can be an issue at a treatment plant. So obviously we have a restroom here, a men's room, where we have a lot of urinals, and again, with low flow toilets, we may find that this load of ammonia and organic nitrogen entering the wastewater treatment plant can be very high during times when everybody's on a break or at halftime or whatever is going on at that event center. The landfills that we sometimes bring in, the liquid water that has kind of seeped down through the layers of trash and soil, the landfills capture what we call leachate. So leachate is that water that leached down through the trash and all of the garbage, and it's rainwater that has seeped down and was captured by the liner at the bottom of a landfill. So the leachate has to be treated in some cases, and some cases it comes to a municipal wastewater plant. Now, the leachate itself has a lot of different components to it. I can't go into in depth on all the different types of compounds and chemicals that would be found in there, because they're mostly all a little bit different depending on what's in that landfill and the age of the landfill. But I do want to say that a lot of organic nitrogen and ammonia makes its way into the leachate. So we have decaying and decomposing trash that is converting things back to their base elements. And in some case, during this anaerobic processing that's happening inside the landfill, which is also producing methane and hydrogen sulfide and all those gases, we're also producing unionized ammonia and ionized ammonia in the form of ammonium. So this leachate then has to be dealt with, and it could do it at the landfill, or we can actually try to treat it at our municipal wastewater treatment plants. And so we find that this leachate can be very high in ammonia and ammonium, and we want to handle that appropriately at the treatment plants ourselves. If we can bleed that into the plant slowly in a controlled environment, like pump it slowly into the treatment plant under our own, when I say our own as operators, under our own conditions, when we can kind of control that instead of slug loading it, the treatment plant tends to handle it a little bit better. The anaerobic digesters that we have in some plants can be very high in ammonia in the supernate. So that supernate, like you see in this picture here, this fluid coming in here into sample point number 13, is from an anaerobic digester. So it's flowing into here at a very high amount of ammonia, and we consider some of that also biochemical oxygen demand. BOD is flowing into the headworks of the treatment plant. So these are ammonia loadings that can be considered slug loads of high ammonia or ammonium. So we talked a little bit already about alkalinity, and I stress that alkalinity is important. Now, one thing I want to mention here is that we are dealing with nitrifiers. I'm going to write up here on the slide. We're dealing with nitrifying bacteria, and we generally consider these guys to be nitrifiers. And remember, it's two groups of organisms, the Nitrosomonas and Nitrobacter. So the nitrifiers will attempt to use the ammonium. We're going to put ammonium NH4 and NH3. Remember, some of it's NH3. So they're going to use these as energy. They're going to get energy by breaking this down with the presence of oxygen. So we know that oxygen in general is going to need about 4.6 pounds of oxygen just to do this process. But nitrifiers with ammonium or ammonium and oxygen, plus something known as alkalinity. And in this case, I'm going to put the symbol here is going to be bicarbonate, HCO3, little negative. So the bicarbonate comes from the drinking water source or bicarbonate alkalinity that we add into the treatment plant with, along with the wastewater. Sometimes we have to supplement the alkalinity. So the alkalinity is generally found in the form of bicarbonate, and the carbon on this is really what is the driver force for these organisms. So the carbon is used, which releases some more hydrogen into the water, which then can actually start to produce some more acids, which can then drive the pH down. So if they're consuming alkalinity, which is generally a buffer for us, and there's some acids being produced, then we're going to run out of alkalinity in a pretty quick pace. So the pH can stay stable for a very long time, but once the alkalinity is dwindling or diminished, then the pH can start to fall because we're having so much excess free hydrogen producing acids in the water. So alkalinity is a buffer against that acid formation, or consider it a neutralizer. So nitrifiers plus ammonium plus oxygen plus bicarbonate will help us produce, in this case, remember the final products that we're talking about today are nitrite and then finally to nitrate. So we're going to be forming, this is a negative, we're going to be forming these along with other acids and more bacteria and even molecules of water, by the way. So the a ratio, or the amount of alkalinity that's used up in this process, is shown here. It's approximately 7.1 pounds of alkalinity used up for every 1 pound of ammonium that's being oxidized. So this is a big number. This is a lot. We know that alkalinity comes in the wastewater from the potable water source, but there may be times when we just don't have enough to supplement the amount of nitrification that needs to take place. Let's see if we have we don't have a slide here. I was going to say, let's see if we have a mathematical slide to kind of show you, but I'm going to show you it right here. So if we have 7.1 pounds of demand on the alkalinity for every 1 pound of ammonia coming in, or 1 part of ammonia, then we're going to use up a lot of our alkalinity. Let's just say, for instance, here on the bottom of the slide, let's say that our influent, let's say influent NH3, because we're talking about ammonia, we're just saying ammonia, is going to equal, let's say we have 39 milligrams per liter of the influent ammonia coming in the plant. And we also have some organic nitrogen. So I'm going to put organic nitrogen here, because you learned today that the organic nitrogen also gets ammonified and gets converted into ammonia that has to be then subsequently nitrified. So let's say that the organic nitrogen is 12 milligrams per liter. And this is going to be coming into the treatment plant that will need to be nitrified. Now, we generally say that the ammonia and the organic nitrogen is what we call TKN. So if we have 39 plus 12, we have essentially, this equals 51 milligrams per liter. And we're going to call this TKN because that's the sum of the ammonia and the organic nitrogen together. Now, this is going to have to be nitrified in order for us to meet low levels of nitrogen in our effluent. So let's say we have to meet a less than 3 milligrams per liter total nitrogen. We're going to have to convert this into nitrate and then denitrify it later on. So we got 51 milligrams of TKN coming in, and we're going to try to nitrify all of that. And we're going to use 7.1 pounds of alkalinity for every 1 part. So let's say 51 times 7.1, and I'll put here milligrams because we're dealing with milligrams as this unit's milligrams. So let's say 7.1 milligrams of alkalinity. And how much total alkalinity will we need then? So 51 times 7.1, I come up with 362.1 milligram per liter as total alkalinity that will be needed to nitrify this. So we do want to pay attention to how much alkalinity we have coming into the wastewater plant, because we're going to need, in some cases, to supplement it if we don't have enough. If I measured my influent of alkalinity, I'm just going to put influent alk here, is, let's say, 250 milligrams per liter. Well, then you can kind of see right here, we have a shortcoming of quite a bit. So if we take off the 250 from there, we're lacking, we are in deficit of alkalinity as far as 112.1 milligrams per liter in deficit. So we are in the red. We are in the red on this. So now we're going to have to pay attention to how much alkalinity is going to be consumed throughout the process. You will learn here today in my discussion with you that denitrification gives us some of the alkalinity back. So if we successfully denitrify this nitrate into nitrogen gas, we will gain back some of the alkalinity, and it may be enough to offset that 112.1 that we're looking for. Plus, we also want, don't forget, we also want some remaining or some buffering alkalinity at the very end of the process. Our process engineers and experts in the field tell us that we'd like to see somewhere between 50 to 80 milligrams of alkalinity just remaining, just left over, so we have enough to keep the pH from decreasing too much. So we don't need to just supplement 112 milligrams per liter. Let's add on to that another 50. We would really like to see about 162 milligrams per liter as buffer capacity. So we're going to need more of it than what we show here. So the slide tells us right here that low influent alkalinity may require some chemical addition. The chemical that we're talking about here is calcium oxide, usually lime. We call it quicklime, or hydrated lime, which would be calcium hydroxide. We can also use things like magnesium hydroxide, sodium hydroxide, soda ash are things that we could use to supplement it. But what you can see right here on this slide is that we are going to be in deficit of the alkalinity if these are our total numbers coming in the plant. And I do want to point out to you guys listening to this that don't just think you only have to deal with the 39 milligrams to be nitrified. You still have the organic nitrogen hiding in the background that will be ammonified and then have to be nitrified and removed as well through these processes, especially if we're going to meet low total nitrogen numbers. All right, so we've got a lot of stuff going on here on our slides. So our next slide shows us some of these additional chemicals. We have sodium hydroxide, which is, we're going to say NaOH. We sometimes call that caustic soda. Soda ash is NaCO3, and sodium bicarbonate. Sodium bicarbonate is basically baking soda, which would be NaHCO3. So bicarbonate, soda ash, sodium carbonate, and sodium bicarbonate being baking soda. Lime is CaOH. Lime is calcium oxide rather. So lime is CaO. And we can also have magnesium hydroxide. I'm going to write this up on the slide here. Magnesium is another one that's used. Magnesium hydroxide can be utilized. That's another good chemical, sometimes used for odor control in the collection system. And ammonium hydroxide is also available. We don't really want to add more ammonia to this because then we're going to add more work for us to do with as far as a treatment plant. So those are the more common chemicals to see us use in the treatment facility. I'd say that lime is by far the biggest bang for your buck. You're going to get the most bang for your buck as far as available alkalinity, but it's a little bit messier to handle in some cases to prepare into a slurry and then pump into the plant, where sodium hydroxide or caustic soda is something that can be purchased as a liquid already and pumped in a little bit more efficiently. But again, this is depending on what chemicals you have and what is available to you and what you would rather deal with. But by far, lime is the more common chemical to use, and you see it written in red there to just kind of express that lime is a good one because of the available hydroxide alkalinity and the calcium that adds a little bit of a buffer for the wastewater. All right, so let's talk a little bit of the troubleshooting. So again, remember what I said, this was what we call an abridged version or a condensed version of nitrogen removal on the nitrification side of things. So we're kind of keeping it somewhat aimed towards your exams, things like that. But if you want to learn more about all of the intricate details and all the moving pieces that are hidden behind the scenes a little bit further into the discussion, that's some of the stuff that we teach here in our classes on BNR operation at the University of Florida Trio Center. You can also read a lot of this on your own and find a whole bunch of other material out there. Some really great manuals out there. MOP number 29 from the Water Environment Federation is another great book on operation and maintenance of biological nitrogen removal facilities or nutrient removal facilities. So let's talk a little bit about the troubleshooting here. You can kind of see we have a pretty good list. This list is also represented by what we said that were factors that affect nitrification. So the observation on this troubleshooting guide says that we have nitrification problems, high effluent ammonia or TKN. Remember that TKN is equal to the organic nitrogen, ORG, organic N, and the ammonia added together, those two added together. So if we have high organic nitrogen and ammonia, or one of each or one of the other, then we have high effluent TKN. So what can cause high effluent TKN? Well, number one on the list is the influent alkalinity being too low. It says here that's probable cause A, not enough influent alkalinity. It says check the influent alkalinity. We will need about 7.1 milligrams for every 1 milligram of ammonia that's going to be oxidized. If we don't have enough alkalinity, we're going to add some alkalinity in the form of lime, sodium bicarbonate, or sodium hydroxide. Remember, we said sodium bicarbonate is baking soda, and sodium carbonate is called soda ash, and we said sodium hydroxide is known as caustic soda. All those contain hydroxides or forms of chemicals that will raise the alkalinity up for us. The next one on the list, the influent pH. We have to check the influent pH, because if it's too low, then we're going to have problems in the process, because we're also going to produce acids in this, which drive the pH down even more. So we got to have enough or high enough influent pH. It should be between 7 to 9. I would say that most domestic wastewater plants are between 7 to 7.5 on the influent, which is generally in the right range. So if normally pH problems will be with a low pH, addition of alkalinity would help with that. The temperature, we said temperature plays a big part. I do want to mention here that the optimum range is somewhere between 30 to 50 degrees Celsius. Now, if we're up around 40 to 50, we're going to start to have some higher temperature issues, but the optimum range is somewhere up around 30 degrees, and that's going to be a warm mixed liquor temperature. In some plants in the United States, we may not see it get that high, even in the highest temperature ranges in the summertime. So having a temperature somewhere between 20 to 30 degrees Celsius is kind of more normal in some areas, but as we get cooler, as the temperature gets closer to that 20 degrees C, we're going to start to see a definite slowdown of the bacteria not performing as fast. It says monitor commercial industrial discharges for too high of a temperature, but also pay attention to the regular seasonal temperature changes. Monitor the mixed liquor temperature with your DO meter or your constant read analyzers. You generally have a way to measure the mixed liquor temperature, several different methods there. Maintain or raise the mixed liquor numbers up, the milligrams per liter up, during colder temperatures to keep the right amount of bacteria present to do the job. The DO is important. Obviously, we have to have sufficient DO. It says typical guidelines are between a minimum of 1 milligram per liter to an average of, say, around 2. And we're saying there that anything over 2 is really not necessary for nitrification. You don't want really less than 1 in most cases to get good, full, efficient nitrification, but doesn't mean it won't happen if you have less than 1. So typical ranges are around 1 to 2 in that 1 to 1.5 range. If the DO is too low, obviously raise the DO up. If it's not in that range, if it's too low, we'll say less than, let's say around 0.5 all the time, you may limit the amount of nitrification. It also says here that 4.2 pounds of oxygen are required to oxidize 1 pound of ammonia. I used the number a little bit earlier, 4.6, and that came from the Biological Nitrogen Removal Manual. So this one says 4.2. So you guys get the idea that we're going to need quite a bit of oxygen to make sure that we're getting enough nitrification. It says check blower operation. It must deliver enough oxygen to nitrify. So that's the pounds of oxygen being transferred into the mixed liquor. The sludge retention time, the SRT, there's a couple things here. Don't forget that SRT is the days of sludge age, but we're also going to talk about retention time in the actual process. So the first thing is the definite sludge retention time or solids retention time to actual mixed liquor temperatures. The SRT must be higher at cooler temperatures due to reduced microbiological activity. We know that the MLVSS gets too cold during the wintertime. We're going to need more of those bacteria to do the job. And it even says here in cold weather, increase the SRT, which means reduce the wasting rate. So build up your MLVSS. You want to base this on pounds of MLVSS, not just the MLSS. MLSS is the total amount of suspended solids. MLVSS is more about the organic portion of that MLSS. So we're going to try to raise up the MLVSS during cooler seasons. We're also going to maintain the right hydraulic retention time, and that's the time through the basins. If we're going through the basins too fast during the peak loadings of the day, we're going to shorten the detention times in the process and not have enough time to fully nitrify. So you're also going to check the HRT, which we're going to call hours. This is going to be hours of detention time. And the last thing on this list is check for influent toxicity. Certain heavy metals and organic chemicals are toxic, and obviously watch out for pesticides, herbicides, cleaning compounds, antifreeze, all that fun stuff. Remember, I'm going to add onto the list here chlorine used for bulking sludge control. Watch out how much chlorine you add to try to control one set of bacteria problems, and you could create another set of bacteria problems. So you definitely don't want to do that. You got to watch how much chlorine we add for purposes within the treatment plant, just to say, well, we're trying to control a settling problem. So just watch out for that. All right, it's a pretty healthy list. Obviously, the big takeaway highlighted is the alkalinity. We tried to stress that through this whole discussion about how important alkalinity is. So when we come back from a short break, I'm going to take a quick break here. I'm going to get into denitrification with you guys. So we're going to break for just a few moments here. I'll get another sip of coffee, and I'll see you back on the other side of the break. All right, welcome back from the break. And we're going to talk now about denitrification. So this is going to be a conversion of the nitrate that was made during the nitrification phase. And we're going to convert that into nitrogenous gases like nitric oxide, nitrous oxide, but really ultimately nitrogen gas. And this is going to be known as a reduction process, whereas the nitrification phase was known as an oxidation process. So we're going to be introducing to you a term called oxidation reduction potential, or ORP. So we'll talk about that a little bit here as far as how to monitor the denitrification basins, or where we're purposely trying to have it happen, or if it's happening, in a basin where you believe it should not be occurring. Let's say you're getting denitrification in a clarifier and you're experiencing pop-ups or problems in the clarifier, then we can use ORP to kind of see if we're in the range for either an oxidative situation or a reducive situation. So we'll talk about that. So denitrification is the reduction of nitrate to a final product of nitrogen gas, and we're going to be producing some CO2. We're going to be producing a little bit of alkalinity here, and some molecules of water and energy for the bacteria to grow and reproduce. So this is going to be taking place in what we call an anoxic basin, or during a time when there is no free available oxygen, which is the term anoxic. It means not oxic. So we go back to our nitrogen cycle slide. And remember that we started off at the top corner here with the introduction of the urea into the waste stream, and we ammonified by microorganisms. That was through decomposition and hydrolysis. And we ended up over here at the ammonia, and we said that some of that was ammonium. And and it depends on the pH and the temperature and the collection system and all that. And we nitrified, we kind of came this direction and we went to nitrification, and that took place in the aeration basins, and that was in an oxidative state. And then we did the process again, finished off the nitrification to make nitrate, which was the fully oxidized version of the nitrogen with respect to oxygen, 3 oxygens and 1 nitrogen atom, making a compound known as nitrate. And we called that nitrification. So that was all during oxidation processes. So for this particular presentation, or this part of our presentation, we're going to be talking about a reduction. So the nitrate is now going to be reduced. We're going to keep reducing through the processes called denitrification. We're going to break this apart and take this molecule of nitrate and break it into smaller components until finally we end up with nitrogen gas, which is what we're going to talk about here. This is where we're going to end our discussion, because we're going to be putting the nitrogen gas back in the atmosphere. So we won't really get into the nitrate assimilation or the nitrogen fixation or any parts of that in this presentation. All right, so what do we need for true denitrification to occur? Well, we have to have some nitrate or nitrite present. We have to have what we call an anoxic environment. We have to have an environment that has no free dissolved oxygen available for these organisms to utilize as an oxygen acceptor or oxygen source. We want them to look preferably to the nitrate or the nitrite. Now, if this is happening in a part of the treatment plant where we don't want it to happen, and we're experiencing pop-ups and ashing on the clarifier surface, that type of thing, then we want to recognize that there is the potential for nitrate to be being used by the bacteria as a oxygen, let's say an alternate oxygen source. And so an anoxic environment could take place in a basin like a clarifier, or down in the sludge blanket. It could take place in other parts of basin. It could take place in the aeration tank if you're not aerating enough and you have areas of the aeration tank that are actually considered anoxic. And in some cases, some treatment plants operate specifically for that, so that they can have what we call simultaneous nitrification and denitrification. So just by manipulating the oxygen in certain parts of your basins, or making sure that your DO isn't too high in some areas, you may actually be making an anoxic zone inside of a basin, specifically for this. So we're going to talk about what that is. An anoxic environment is very important. We're going to need carbon for these bacteria. The carbon source is going to be supplied to these bacteria in the form of the sewage, the organic components that we're sending down the line, down the pipeline into the treatment plant. So this is going to be a carbon source is going to be raw sewage. In some cases, we have to supplement carbon in the form of a chemical known as maybe methanol or acetic acid or acetate. Glycerin glycerol is sometimes used. So we have different types of carbon that we'll talk about. And then lastly, we have to have the proper range that bacteria need for environmental conditions to be just right for them to reproduce, which is again the pH, temperature, and all that to be at optimum. So we won't go too far into those, since we covered that during the nitrification part. So the first thing we want to talk about is an anoxic environment. So this means anoxic, or AN means not oxic. So there's no free DO present. Dissolved oxygen is going to be at as close to 0 as you can get it. We really don't want free dissolved oxygen there, because these bacteria are going to be asked to take nitrate and nitrite apart and reduce it And if there is oxygen present, then there's no real motivation for them to do this because we're supplying them with oxygen. So they're going to be doing their metabolism through an oxidation process rather than an anoxic process. So we don't want free dissolved oxygen in this basin, or if it's happening in the clarifier and it's happening where you don't want it to happen, then you know that there's no free dissolved oxygen in there. We do, however, want or would like there to be some nitrate or nitrite present. So for us to successfully denitrify the nitrate, then we need to give that oxygen source, let's call it a combined oxygen source, to these bacteria. And if we give them some oxygen in the form of a bound oxygen like nitrate or nitrite, they will be able to utilize that in their desire to break down the carbons that are coming into the basin or that they're presented with. So these bacteria are considered facultative. So this term is an important term. Facultative for our discussion today means that they are able to be either metabolize or use carbon in the presence of oxygen or in the absence of oxygen. So they don't have to have oxygen present for them to metabolize and use carbon. So carbon is coming in the treatment plant in the form of the raw sewage, or it's the carbon that we're supplying them with a chemical, an alternative chemical, methanol, acetic acid, that type of thing. So then these bacteria are the massive amount of bacteria that we have. We talked a little bit earlier about the aerobic bacteria, these nitrifiers that we talked about a little bit earlier. And we said that nitrifiers, I'm just going to kind of write up here on the slide real quick, that nitrifiers, the nitrification process, nitrifiers, they made up about what we said, about 5 to 10%. I'm getting a little sloppy here, 10% of the MLVSS, that was the nitrifiers. Well, these bacteria, these facultative heterotrophic bacteria, make up roughly about, let's say, 90 to 95% of the MLVSS. So these bacteria are a huge amount of the population. So there's so many of them present, and they're willing to utilize the carbon either in the presence of oxygen or with a lack of oxygen, that we can make this actually happen. One of the things that I want to stress here is that this is found within the MLVSS, and because we have so many of these bacteria available to do this job, the anoxic basins or the anoxic areas of the facility or even in the flock itself can be smaller because there's more of these bacteria present to do the job. So the hydraulic retention times are necessary to be the correct number, but obviously they are going to be a shorter time because we have so many more of these bacteria as compared to the nitrification side of things. So these bacteria will utilize oxygen in the following order. And now remember that this is so that they can consume or oxidize carbon that they are trying to consume and use for growth and reproduction. So if oxygen's present, this is number one on the list. Number one on their list is oxygen. They say we have free dissolved oxygen, we're good to go. But if we take away the oxygen and actually, so to speak, suffocate them so that there's no free oxygen there, they will use an alternate enzyme within their cell to be able to reduce or chemically break apart a bond of the nitrogen and the oxygen within the nitrate molecule and gain some of that oxygen from it. So number two on the list for the facultative organisms would be nitrate, and we can actually add onto this nitrite because NO2 is carrying oxygen with it as well. So nitrate and nitrite is available. So it's on the list, and they would use that in that preferential order. So no DO and nitrate or nitrate present, they will be considered anoxic. If we go down the list and we take away the nitrate and nitrite, if that's no longer available, then the bacteria, the facultative heterotrophs, will start to utilize sulfate as a oxygen source, sulfate and sulfite. So where does this generally happen? So this generally occurs in the collection systems, and I can kind of point out a few things here. This is usually occurring in collection system, and we call that the sewer system. And the bacteria are generally not given a whole lot of free dissolved oxygen out in the sewer system. They're not usually given much nitrate or nitrite because that's considered an oxidized form of nitrogen. And so these bacteria are generally in what's considered a reducive environment. So more capable of reduction than capable of oxidation. So bacteria that are facultative and surviving in a reducive state are able to break apart these compounds into simpler forms. So if there's no nitrate or nitrite present, they can take the sulfate and start stripping away the atoms of oxygen from the sulfate. And what generally occurs then is we have the production of hydrogen sulfide gas, which is generally a gas that smells like rotten eggs and causes the formation also of H2SO4. So we know that that is sulfuric acid. And so the acids that can be formed can drive the pH of the influent wastewater down and also produce acids that would eat away at concrete pipes, iron pipes that aren't protected. We can start to have degradation of the headwork structures. We can have, concrete crumbling apart in manholes and the sewer systems in general. So H2S and H2SO4 are generally found in collection systems that are somewhat what we call anaerobic or somewhat septic. And it's because there's none of the number 2 or number 1 present that these bacteria then go after the sulfate. So a way for us to prevent the odors in some cases then would be to supplement, say, nitrate in the water. And so some chemicals are on the market that actually provide a form of nitrate into the chemical that then is injected in the collection system, and the bacteria then say, okay, well, I'll use the oxygen off the nitrate and I won't bother to make hydrogen sulfide. So a chemical with nitrate on it could actually inhibit the odor production in the collection system because we're providing them a form of bound oxygen. Another chemical that's sometimes used is an actual form of oxygen, which is called H2O2, which is known as hydrogen peroxide, which also gives the bacteria some oxygen. So H2O2 is peroxide, and another chemical that's used to supplement oxygen out in the system is called potassium permanganate, which is KMnO4, which is also providing some oxygen in the form of its chemical. So different forms of oxygen and nitrate can be provided to prevent odors in collection systems. If we're not adding these chemicals to the collection system, then the bacteria continue to consume or convert the sulfate into sulfides and produce the sulfuric acid. Number 4 on the list, again, if conditions are appropriate for the bacteria, we start to get the usage of carbon dioxide, and this generally happens in very reducive environments like digesters and again, collection systems that are somewhat or very anaerobic. So these are done by facultative bacteria, and what our job is today is to talk more about this reduction of the nitrate in the form of an oxygen supply for our bacteria. So that's what we're looking at. So when we say the DO level must be below 0.2, what I'm telling you here is that we would really like to see this in the 0.00 range, which would be optimum. And so some of our DO meters have trouble reading all the way down into those numbers. So we've generally gravitated towards saying, like, if we're less than 0.2, which was the minimum number on the old analog DO meters, that was the very first little line on the analog display. We didn't really know how low we were on some of those models or or those instruments. So digital meters today, and especially the luminescent dissolved oxygen or the fluorescent dissolved oxygen probes that are on the market, can read down into the hundreds of parts of dissolved oxygen. And so it's common for us to see ranges in the 0.05 to 0.02, which is down very low. And again, it's down near the bottom limits of these meters to measure. So we generally say the DO must be as low as we can possibly get. We have to have some nitrate present, nitrate or nitrite present. So we have to have that. Remember that the oxygen is going to be looked at by these bacteria for their oxygen acceptor. And another term that we use in anoxic basins and also in checking to see if we are in the actual anoxic range is using a measurement called ORP. And ORP is oxidation reduction potential. It's the potential of the water or the mixed liquor or the environment that we're measuring to be either oxidative or reducive. So if a lot of free dissolved oxygen is present and a lot of nitrate is present, like say in an aeration basin, the ORP numbers are generally in the high millivolt range, which means positive millivolts, somewhere above 100 positive side of the millivolt range. That would be aerobic. And anoxic is generally considered somewhere in the range of plus 50 to negative 50 millivolts. Now this is measured as MV on an actual ORP meter. And I'll explain just a little bit more here in just a minute. Mixing is very important. We want to keep all of the bacteria together with the carbon source that's coming in. The carbon is going to be utilized by the bacteria as their organic carbon, and they're going to want to break that down for their energy and in their diet, their carbon source in their diet. So we're going to mix them all together and keep everybody, in intimate contact with each other. And we want to watch out for any dissolved oxygen in the return streams. Return streams means internal recycles. A lot of our treatment plants have internal mixed liquor recirculation. So I'm going to put internal recycle, and this can be within its own treatment plant in some of our processes that have internal recirculation. And we also have an RAS. This is the return activated sludge back into the treatment plant. So we want to watch out for dissolved oxygen in those two. And then any dissolved oxygen in what we call in-plant side streams. So in-plant side streams are things like belt press dewatering, fluids, centrifuge fluids, any kind of sludge dewatering. When we drain tanks back to the head of the plant, we have in-plant side streams. When we supernate digesters, we supernate aerobic digesters or anaerobic digesters, we have this fluid coming back into the plant. So these are all in-plant side streams and in-plant return circulation or recycle systems. So here's an example of a basin that's set up for what we call pre-denitrification. So this is using, I'm going to kind of write it on the tank picture here, but this is using a process called the MLE process. That stands for Modified Ludzak-Ettinger process. So it's also known as pre-denitrification. So when we talk about pre-denitrification, we mean that we're going to denitrify first, and nitrification. And what we're going to do is take the nitrate and present it as an oxygen supply to the bacteria in the presence of all this organic food coming in, and ask the bacteria to take the nitrate and convert it into a form known as nitrogen gas. So hopefully coming off of this into the atmosphere is N2 gas. That would be coming up into the atmosphere. N2 is coming off of this basin back to the atmosphere, but the flow is actually going from this basin into the aeration tank, which you can kind of see by the large red arrows there. So the flow is actually the first thing coming into the plant is actually into the anoxic basin, which kind of leads some people to say, well, now wait a minute, in order for us to get nitrate for the anoxic basin, we have to nitrify first. How can we then have nitrate available at the beginning of the plant if we're trying to denitrify first? That doesn't make sense. So in the MLE process, or the Modified Ludzak-Ettinger process, there's a series of pumps. and a pump is usually near the outlet end of the aeration basin, some kind of mixed liquor return pump. And we pump back to the beginning basin here, the nitrate rich mixed liquor from the back end of the aeration tank. So in the aeration tank, we actually form the nitrate. We're going to put nitrate NO3 back here, but way up here in the beginning of the tank, it's NH3, which is ammonia. So we know that the process goes ammonia at the right rate. So we go NH3, NO2, and NO3 in this direction. And now we're going to recirculate a whole bunch of this nitrate back through and put it back in the anoxic tank. So that's kind of the layout of what's called a modified Ludzak-Ettinger process. And the reason that it's very popular, I think one of the reasons is that it utilizes the organic waste coming into the treatment plant known as sewage as its carbon source. So we're not having to purchase as much of an external carbon, say in the form of glycerol, acetic acid or acetate, methanol, those types of things, some kind of simple sugars that can be used to give the bacteria the carbon that they need. So we're trying to save, getting to save some money because we're using the sewage as the carbon source. But the process is known as pre-denitrification. So it's kind of an interesting scenario. Now, what happens to the ammonia that came into the treatment plant? So if we're coming into the very first basin, and it's called an anoxic tank, and we have ammonia coming in here, and I'm going to put NH3 because that's kind of the general term, but remember it's usually NH4 plus. So that's coming into this basin, but since it's not aerated and there's no oxidation present, hopefully, then we're not going to really do anything with that ammonia or ammonium. It's going to stay relatively stable or constant through the basin, and it's going to migrate its way into the aeration tank. So the first basin in the process doesn't do a whole lot with respect to the ammonia or ammonium that's present. At least it shouldn't, because we're not actually aerating that basin and we're not supplying that 4.6 parts of oxygen needed for nitrification. So it's all about denitrification in that very first basin. All right. So here's another example of a pre-denitrification tank. So there's a lot of these processes around the United States and around Europe known as the carousel process. So it uses an oxidation ditch type setup where we have a pre-denitrification basin ahead of the carousel, or we'll call it the oxidation ditch process. The oxidation ditch is kind of on the other side of this wall here, and this is where the big mechanical aerator is putting oxygen into the tank. But there's a mixed liquor flow of water flowing from that anoxic, or from that aeration basin, into this anoxic zone, and coming from the side of this basin where we have some actual nitrate in the mixed liquor. So we start to see the denitrification take place in this first basin. So if we have NO3 coming in to this basin and influent wastewater, and put over here influent BOD coming in, that's the carbon coming in. So now we start to get the nitrogen gas, the N2, coming off the surface. So N2 going back to the atmosphere. So we're starting to reduce that nitrate into nitrite. This goes to nitrite, and then to N2O, and then finally to N2, which then comes off as a bubble. So that's the process of denitrification taking place in this mixed tank that is gently mixed so as not to produce any oxygen in that basin. So it's the first stage of the carousel plant is actually set up as the Ludzak-Ettinger process. So an interesting thing with producing nitrogen gas from nitrate, we will actually produce some alkalinity in the form of either carbonate or hydroxide alkalinity when we successfully denitrify. And remember, we said earlier in this discussion today that we talked about nitrification, and we said alkalinity was a huge part of nitrification because we were going to use up so much of it. There was like 7.1 parts of alkalinity used per 1 part of ammonium. So we said that that was a huge amount of demand on alkalinity, but now we're actually going to recover about half of it. So the number that we generally attribute to this is around 3.5 parts of alkalinity per part of NO3 that we reduce to nitrogen gas. So around 3.5 parts of alkalinity are produced. So this is where we gain some alkalinity back. And if this is at the head of the treatment plant, then we actually have a boost of alkalinity occurring along with the alkalinity coming in, and we actually see then a supplemental amount of alkalinity present before the aeration tank, which then gives us the amount of alkalinity we need for nitrification. So when we successfully denitrify, we gain back some alkalinity, and many times the treatment plant operators never really notice any problems due to an alkalinity deficiency or even a pH drop, because the pH never really got to the point where it would drop, because there was always alkalinity present to prevent that from happening as the buffer or the neutralizer. So alkalinity recovery is a very big benefit of successfully denitrifying. So when we mix the tank, we incorporate into this anoxic basin, we're going to incorporate 3 waste streams. We're going to incorporate the influent sewage, and I'm going to put influent sewage. That's going to represent our carbon source, the influent sewage, or if you have a primary clarifier, it would be the primary effluent into this basin. So the influent sewage contains the BOD and the CBOD. That's the carbon that we need coming in. It's essentially the CBOD we're looking for. We're going to have the return activated sludge that came from the clarifiers in the back part of the plant, and we're going to have an internal, I'm going to put an internal recycle, and the internal recycle is going to be MLSS with nitrate in it, NO3. So I'm going to put that MLSS plus the nitrate in it is inside the internal recycle. The return sludge is the actual settled bacteria, and the influent sewage, all of this blended together makes what we call MLSS. And generally the first basin of the MLE process, or in subsequent basins downstream, we generally keep it mixed because we want to make sure that we're not allowing any oxygen in there. We don't want it mixed with aeration. We want it generally mixed, gently mixed, and we don't want to induce any oxygen in there. And in some cases, if this anoxic basin is further downstream, then we may not have enough of the carbon coming in, and we may have to supplement that to make that actually work. And that's kind of more common in the 4-stage Bardenfo type of situations, the AO processes, the A square O processes, or say other BNR facilities that may lack enough carbon downstream. So we may find that we have to produce or give them some extra carbon, actually purchase it rather. So mixing is very important. It allows intimate contact with the food and the return sludge, and produces the mixed liquor. It does allow for adsorption and absorption of the food, and that is the facultative heterotrophic bacteria. These are bacteria that can survive with or without free oxygen, and their heterotroph means that they're actually getting their carbon from a supplied carbon source that is us as humans have supplied them this food. And so we're giving them the carbon already in a pre-made fashion. They don't actually have to produce their own energy from chemical sources like the nitrifiers did. These heterotrophs are given the carbon that they need. So the carbon is generally, for most of us, is going to be the influent wastewater that has been screened and degridded, or if it's been through a primary clarifier as well, it's going to be the primary effluent flowing into the first biological treatment basin. So the carbon is going to be the CBOD, which is carbonaceous biochemical oxygen demand. Carbon food or food sources, the most common on the list is raw wastewater. This is where the MLE process, or the modified Ludzak-Edinger process, takes advantage of the influent wastewater as the carbon source. So its placement of the anoxic basin is to aid the ability of these organisms to do this job without having to supplement additional carbon. Downstream in other anoxic basins or in clarifier sludge blankets, sometimes we find that bacteria rely on their own carbon within their cells to continue to survive. And so we call that endogenous carbon. Endogenous carbon is supplies of carbon within their cells that they have, like food storage vacuoles that they have that they've stored with carbon in it, and they're using for their energy to reproduce. And so endogenous carbon is sometimes burned up within the cell when they're kind of left alone down in the sludge blankets of clarifiers, especially with deep clarifier sludge blankets where the actual settled sludge starts to get anoxic. Remember that when it goes anoxic, there is the potential then for them to strip away the oxygen from the nitrate. So if they go anoxic and there's endogenous carbon from within the bacteria, which there generally is, then we'll start to have some denitrification occur. The next one on the list is called methanol. Methanol is highlighted here because it's a common food source, or carbon source rather, used in wastewater treatment plants that supplies what we call a simple, easily assimilated carbon. It's known as a wood alcohol in some cases. Methanol and ethanol are carbons that can be taken in by bacteria somewhat quickly and can be dosed kind of accurately. If we know how much nitrate and nitrite that we're trying to reduce, then we know how much BOD is left over, and then we can figure out how much of this external carbon to add. We can accurately dose the methanol based on those numbers. We'd also have to measure how much dissolved oxygen is present, because that's going to be used first by the bacteria in the oxidation of the methanol rather than the denitrification of it. So or purposes rather. So methanol is commonly used. It is a hazardous chemical, and I do believe that you should be very knowledgeable of these chemicals that you're feeding and using at the treatment plants. You don't want to overdose them, and you don't want to handle them with disrespect. You want to handle them very carefully, because methanol is a flammable compound and can cause harm if mishandled. Another one on the list is acetic acid. Obviously, the word acid kind of brings to the point that it is similar in case to, like says, say, strong vinegar. And anytime you're dealing with an acid, you also have to have proper PPE and make sure you're handling this chemical appropriately. We definitely don't want to treat acids with disrespect, but acetic acid is another common chemical used, sometimes known as acetate, and sometimes fed into the wastewater to supplement the carbon source. Coming down the list, we see this crazy thing. It says dog food. Why would we feed dog food to the wastewater plant? That seems crazy. Well, in this case, dog food has been used by many operators of small wastewater treatment plants as a supplemental carbon source when there is not residents present to feed the wastewater treatment plant with enough carbon or carbohydrates. So some operators have been known to purchase bags of dog food, and we have just kind of as kind of a laugh out loud type of joking thing, say Old Roy, which is kind of a dog food it's commonly available at an inexpensive cost. And so if that is crushed up or fed into the treatment plant in a powdered crushed up form, or even put into the lift station and allowed to dissolve in the influent lift station, it will feed the wastewater plant the carbohydrates and supplements carbon that it needs. And so dog food has been added to lift stations, to the small package plants when, like, schools are in summer recess, or when Christmas shut down or spring breaks, that type of thing. When we don't have the carbon coming in, then we may want to add a supplemental carbon source to keep the bacteria alive and somewhat healthy, so that they're ready to go when the human waste starts coming back in. So again, it's not commonly used to say for a large municipal wastewater facility to go and get old Roy dog food, but it is commonly used for small package plants. The more common one to see used in municipal facilities is the methanol, the acetic acid, or I'm going to write on here because I don't have it on my bullet point. I'm going to put glycerin or glycerol. So glycerin or glycerol. So glycerin, glycerol, basically sugar compounds. Oops, this is glycerin. So it can be a sugar compound or a simple product of a chemical that can be fed in there, but it's kind of messy. But you guys get the idea. This is not really such a huge thing for, let's say, an exam purpose. I think for exam purpose, you'd want to know these two off the list, but for operational side of things, you'd want to pay attention to the glycerin glycerol, because a lot of facilities have switched away from methanol due to the inherent dangers of handling methanol because of its flammability. So make sure that's a little bit clearer for everybody. All right, so those are carbon or food sources. So what you really need here, again, remember that it needs to be a simple, easily assimilated, easily brought into the cells of these facultative bacteria. Remember, they don't have mouths. We don't want to feed them chunks of food. We want something that is easily brought into their cells through osmosis. And the carbon needs to be available to them in a simple form that can be brought into the cells somewhat rapidly. We don't want them having to digest or excrete enzymes to break down the carbon on the external parts of their cells, because if this is something that's too difficult for them to break apart, then this could be carried out into the clarifiers or even out into the effluent, which would cause effluent BOD violations or elevated BOD going out in the effluent. So we want something simple that's easy to dose. So those chemicals are generally the methanols, acetates, glycerols, those types of chemicals that can be fed. So what factors affect denitrification? What could limit the denitrification from working its best? Well, the pH needs to be, again, in the slightly alkaline range. We said earlier for the nitrification, it was between 7 to 9. Here it's around 7.5 to 9 standard pH units. So that's a common thing. The temperature and sludge age, we do know that colder temperatures tend to take longer for bacterial biochemical reactions to occur. So the temperature has a direct impact on our sludge ages. So we generally run higher mixed liquors and higher MLVSS during times when temperatures are low. And we also want to make sure that we have anoxic conditions. We certainly do not want DO in these anoxic basins because they're supposed to be not oxic. So we want less than 0.2. We want 0.00 if we can get it. If you're using an ORP meter, you can actually measure ORP as millivolts, and it can be measured with a meter. An ORP meter is a specialized instrument that measures millivolts using a special probe that is designed for this purpose. You can use a pH meter set on millivolts, but you still need to have the ORP probe hooked to the meter. So the ORP probe is a special probe for the purpose of measuring oxidizers versus reducers in the solution. So that range is somewhere between +50 to -50. The carbon source is also related to the process temperature. The colder the temperature, the more pure the carbon source really needs to be. If you're using a process that relies on raw wastewater as the carbon source and it's a cold temperature time of year, then that bacteria action is slower and they're slower to use that carbon. So BOD numbers tend to be a little bit more difficult to maintain in the colder temperatures because of the slow growth and the slow metabolism of the bacteria. So it's related to the process temperature. The more pure it is, the better it will be. Endogenous carbon, if you're relying on bacteria to utilize their own carbon in, say, a downstream anoxic basin, it may not be enough to actually get the whole process working to get the nitrate denitrified. So the quality and quantity of carbon strongly influences the denitrification rate. So especially in cold temperatures. In colder water, things go a little bit slower and the bacteria need a little bit more time, but also a purified form of carbon to really kind of drive this reaction. So there's a term known as nitrite lock. Nitrite lock is a term used to describe a high chlorine demand downstream of the biological process. And this is occurring coming out of the clarifiers into your chlorine contact basins or out of your filters into your chlorine contact basins. But nitrite lock is when a little bit of nitrite actually makes its way out of the biological process and enters the chlorine contact basins. Now, it could be used using bleach as your disinfectant or gaseous chlorine. It really doesn't seem to make a difference. There's times when the nitrification or denitrification process may not be complete. I guess I would try to expound here and just say that the nitrification side of things tends to be where it is more prone to happen. And this is usually during higher flow periods when we don't have enough hydraulic retention time to complete the nitrification side of things. The denitrification part can be an issue, but we generally have a very quick denitrification occurring when everything is right. So it's a little bit more towards the side of the nitrification where we don't actually have enough time. And it's a little bit more prone to see this in, say, the Ludzak-Ettinger processes or basins where we have a flow right straight through the process without a secondary anoxic basin to try to polish off any of the nitrate or nitrite that didn't get quite converted. A lack of Nitrosomonas bacteria or Nitrobacter can contribute. I would say that to produce the ammonia, or rather the nitrite, the Nitrosomonas are taking the ammonia and they are producing nitrite. So this is what's happening with Nitrosomonas. The Nitrobacter, as I mentioned a little bit earlier, are taking the nitrite and producing it into nitrate. So in this particular slide with nitrite lock, we tend to be aimed more here than the other process. So we're kind of caught where we have some nitrite present, but we have not fully converted it all the way to nitrate. So those are some common things to see happen. So the potential here is shown on these different lines of equations. The first line is showing us that when we have chlorine in the form of gaseous chlorine or even bleach, the actual hypochlorous acid that's in there that we're trying to form with chlorine and water producing HOCl is the disinfector that's really killing the bacteria. And it's generally accepted in most of the industry. It's this oxygen that presents itself as the strong oxidizer that kills bacteria. The hydrochloric acid is not quite the strong disinfector that we would like it to be. It doesn't have the available free oxygen that comes apart. Hydrochloric acid is generally ionized as well, so it presents itself a little bit of a disadvantage when trying to break through the negatively charged bacteria, cells, enzymes, and slimes around the pathogens. So the hydrochloric acid is not quite as effective as a disinfectant as the HOCl is. And by the way, at certain temperature and pHs, we can see a dissociation of hypochlorous acid into another form. And sometimes we see this being HOCl and OCl negative. And so hypochlorous acid can convert into hypochlorite ion. And so again, that has another negative charge on it, which is a little bit disadvantage for the killing of bacteria. So we have hypochlorous acid being formed, And if we have nitrite, which is also negatively charged, if we have nitrite present and we put that in combination with the hypochlorous acid, we'll find that we're going to produce or yield nitrate and hydrochloric acid. So we end up with these two compounds formed. So we end up with nitrate. We end up actually producing nitrate from the combination of the chlorine product and the nitrite. So this is happening at the instant when your chlorine is being injected in, or the water is mixing together with the water that has nitrite in it. So here's the thing, here's the end result. We actually produce nitrate from this. The rest of the process happens where hydrochloric acid and water forms hydronium and chloride would be obviously not a disinfectant, excuse me, and we would have hydronium chloride entering the water, which would show us no chlorine residual. So what we ended up doing was using the chlorine to oxidize the nitrite into nitrate. That's kind of the idea of the nitrite lock problem. So many operators notice that the nitrate number seems to go up or be whatever it is, but they don't notice the nitrite. And if you don't measure the nitrite, if you're not measuring this out of the filter effluent or the clarifier effluent, then you won't know if it's the problem or not. So you have to actually measure the nitrite before the chlorination takes place to see if that really truly is the issue with your chlorine demand. So the chlorine is reduced to chloride and hydronium. There's no chlorine residual available at this time. And the chlorine contact chamber sometimes takes on an unusual coloration during this period of time, sometimes a little bit of a haziness, and sometimes a little, looks like a little cloudiness to it. So that's considered the reduction of chlorine being reduced to chloride and hydronium ion and oxidizing the nitrite is the nitrite lock. So the term nitrite lock is given to this, and I just want to point out one thing here, that in most of our manuals we're finding that the ratio of chlorine to nitrite is something like this. It's generally about 5 milligrams of chlorine, of HOCl, to 1 milligram per liter of NO2 to be oxidized. So roughly about 5 parts of the chlorine solution, or what you've dosed, the chlorine that's dosed into the water, not the residual, because you don't have a residual yet, but the chlorine that's dosed into the water and becoming HOCl is going to be used up by 1 milligram of nitrite, about 5 parts. In another manual I saw, it's was somewhere around 9 parts. There's several different books on the available that showed this phenomenon occurring, but the most accepted numbers, I think the most common average to see, is about 5 parts of chlorine being used for 1 part of nitrite, which is a huge chlorine demand, on your actual dose. So you have to overcome that. And many operators see this happen during certain times of the day. And a lot of times it's because we're flowing through the process really quickly during the peak load of the day, and we just don't have enough time in the aeration basins to fully nitrify. So that's what this slide says. How do we avoid nitrite lock? You want to avoid nitrite lock, make sure that you ensure complete nitrification. That is one of the leading causes of this. Ensure that you completely denitrify. Now, it's not as common to see this happen because the denitrification occurs rather rapidly. But if you don't have enough carbon available and you have some of the nitrite making its way out into processes that have downstream or post-denite basins, then you could actually have some issues with it. Make sure you monitor the dissolved oxygen, the alkalinity. The ORP is the millivolts, and the nitrogen series. When I say nitrogen series, you're going to be monitoring this. You're going to be monitoring ammonia, you're going to monitor nitrite, and you're going to monitor nitrate. When I say nitrogen series, that's generally what we mean. You're going to monitor those 3 things because you want to see what forms of nitrogen are leaving the facility, and that would cause you the nitrite lock if you have some of this present. All right, maintain proper detention times in basins. We said that that was the several hours of hydraulic retention time in your aeration basins particularly. All right, and here's our denitrification troubleshooting chart. So we have guide number 8 for denitrification. This is page 2 of the denitrification troubleshooting guide. And the question or the observation says that we have high effluent nitrate. So if we're having some high effluent nitrate, what are the 2 leading causes to make that happen? So one of the leading causes is not providing anoxic conditions. Remember, anoxic means not oxic. And if you have DO present, then you are not anoxic. If DO is present, then you are considered oxic or aerobic. So nitrate needs to be converted to nitrogen gas by these facultative organisms. If there is oxygen present, they will utilize it rather than the nitrate. So it interferes with the nitrate being reduced to nitrogen gas. How do we fix this? If you're using a small plant and you have blowers that are on timers, you can cycle blowers on and off to create an anoxic time period or an anoxic cycle. Sometimes operators of package plants will run blowers on timers so that it comes on and nitrifies and then shuts off and then allows for some denitrification to occur. Make sure you reduce the DO in the oxic zone if it's too high. If you're carrying way too much oxygen in the aerated portion, you could be recycling too much DO back into the anoxic zone if you have too much DO in the aeration basin. And it says lower the DO in the recycle. So that's also part of it, is making sure that the return sludge and the internal recycle doesn't have dissolved oxygen in it. Number 2 on the list, or rather letter B, and this is a lack of carbon source, and that's called soluble BOD. We said that things like methanol and glycerin and acetic acid, those things are simple, more readily usable forms of carbon than, say, raw sewage is. So if we don't have enough soluble BOD present, we may not actually get to denitrify the nitrate that was produced. So we have to have the right amounts of BOD and carbon available, rather CBOD available for the amount of ammonia and nitrite and nitrate that needs to be denitrified rather. So create an anoxic zone at the head of the plant using raw wastewater as the food source. That's kind of the common MLE process where that's pre-denitrification. Provide additional carbon using methanol, waste sugars. Those are, fermented sugars, things like that, that are ethanols or alcohols. And then maintain the pH. Just check the pH, make sure it's somewhere in the range between 7.5 to 8.5 and adjust that if necessary. And make sure you have enough retention time. So remember, we said earlier that we need enough retention time to build up these bacteria. And it even says that microbe activity drops drastically as temperature drops below 20 degrees Celsius. That's about 68 degrees Fahrenheit. And more organisms are required to do the same amount of work when we have colder temperatures. That same thing applies for nitrification, by the way. All right, so that kind of covers our nitrification and denitrification phenomena. Now, remember that in a previous session, I covered what's considered the selectors. So we covered the bacteria basics and the selector technology in the preceding video session of this series. So this is number 2 of 3 in the series. So remember to go back and double check and watch that video if you're not sure what we're talking about. The placement of these basins, the anoxic basins and aerobic basins and all that are covered in the discussion of the selectors as well. But I do have some discussion coming up here, but if you want more information on it, it's also covered in that first session. All right, so here's some questions we have that we like to use in courses, and let's see how you guys do with something like this. So if you wanted to stop the slide here and read this, you can certainly do that, but I'll kind of go through this with you. So as denitrification takes place in the first anoxic zone, what are the expected conditions within that basin? So the first anoxic zone here is like the pre-denitrification basin of, say, the 4-stage Bardenfo or the modified Ludwig-Ettinger, that type of placement. So what would be happening within that basin? Letter A, pH and alkalinity decrease, but nitrate increases. Letter B, pH and alkalinity increase, nitrate decreases, and the ammonia remains about the same. Letter C says pH increases, the alkalinity decreases, and the nitrate increases. And letter D says pH and alkalinity remain the same, nitrate increases, and ammonia decreases. So again, take a second to think about that, and we'll come back and show you the right answer is letter D. The pH and the alkalinity, I think especially the alkalinity, would show a slight increase because we're gaining back alkalinity. We're going to reduce the nitrate, so the nitrate number should drop because we're using it as the oxygen source, so it's being reduced. And the ammonia remains about the same. So going through the anoxic basin, the ammonia doesn't get too much opportunity to be oxidized because there's generally not enough oxygen present for this to occur. So that's why letter B is correct. Next question says the operator is experiencing high chlorine demand in the chlorine contact basin from high nitrite concentration. Which of the following conditions could cause the high nitrite and high chlorine demand? Is it A, high flows through the plant increase the detention time in the aeration tank? Is it B, the plant is operating in the extended aeration mode and should be in contact stabilization? C, the influent alkalinity is 250 milligrams as calcium carbonate? Or D, the high flows decrease the aeration tank detention time? So what's happening in this basin or these basins that could create the high nitrite problem? This answer is letter D, as in delta. The high flows decreased the aeration tank detention time. Remember, high flows during the day could definitely shorten detention times through the basins, which would take away time for the bacteria to do their job. Letter A says high flows through the plant increase detention time, but we know that that's not true because as flows pick up, the detention time decreases. So that is why D is the most correct answer. All right, let's take a look at a few treatment designs, flow patterns that are used to nitrify and then denitrify. The first one is known as the post-denitrification basin, also known as the Wurman process. So a German or Austrian professor and doctor, bioscience doctors with the last name Wurman, came up with this process. And we notice here that we have an influent coming in. Now, this could be the primary effluent or the sewage influent coming into the aeration tank. Now, remember, influent has BOD. That's what's coming in here. We have CBOD, which we know is the carbonaceous biochemical oxygen demand. And we also know that it has TKN coming in the influent. So it has all these different things that we could measure, and that's coming in the influent. So the main thing is the TKN is going to be nitrified through the aeration tank. So we're going to go essentially from NH3, and then we're going to go to NO2, and then finally to NO3. So that's the nitrate. That's what's happening in the aeration basin. The BOD is being used up aerobically because we have a lot of oxygen in here. So there's O2 present. And so we're actually using up the BOD and CBOD in an oxidative process. So the nitrate flows into the anoxic basin, and it says that we would add an optional carbon source. The reason we would add that is because the carbon has been used up in the aeration tank under oxidative processes. So we've used up all the BOD. We're going to have to add something here to kind of get the bacteria in the motivation to use the nitrate as the oxygen source. If we don't add the carbon and there's not enough carbon, then a lot of nitrate will flow into the clarifier and then flow out of the clarifier. So we'd have a lot of nitrate flowing into and out of the clarifier, and we may not actually denitrify as much. So we add the carbon source, and then we limit the amount of nitrate here. Is it going to get it down to 0? Probably not, but it's going to get it down probably less than 5 milligrams per liter, or maybe even in that range, maybe a little bit less, depends on how much time you have available for the anoxic tank to do its job. And remember, the anoxic tank is then allowing the nitrogen gas as N2 to come off to the atmosphere. All right, so the main thing here is that we may have to add an additional carbon source. This may be where we have to add methanol, acetate, acetic acid, glycerin, that type of thing to get the bacteria to do the job. The reason, this comes up a lot in these classes, and I want to kind of tell you something here real quick. The reason we generally don't do something like this, let me kind of draw something here. The reason we don't just take some of this influent wastewater and divert it around to here to use the CBOD in the raw wastewater as the carbon source is because it's not pure. The CBOD is not a purified or pure carbon source. It's easily assimilated. Remember that influent wastewater has chunks or particulate CBOD in it, and it also has some that's soluble, but a lot of it is particulate. It would take time for the bacteria to use as the carbon source, so that wouldn't be as available as, say, a purified source. The other thing I want to mention is that there's also some TKN in here. So we're going to actually be putting in some forms of nitrogen that would then leave in this basin because it's not aerated. So that the TKN would leave the anoxic tank because the anoxic tank is not aerated. So then we would have TKN issues, which is the Kaldol nitrogen leaving in the effluent. So that's not going to work for us to bypass some raw sewage around the basin. So Werman's process worked pretty good, but it needed the extra carbon source. And Ludzak and Ettinger, again, another set of biochemists back in the day, started experimenting with a pre-denitrification tank. So the denitrification tank is ahead of the aeration tank. So notice here that they simply put the anoxic tank first. So the thing that caused this to be called the modified Ludzak-Ettinger is this recycle that was added here. In the original designs, they didn't have the anoxic recycle. They would just relied on the nitrate coming back from the RAS. So there was nitrate here and nitrite here in the clarifier, the solids. And so we recirculated that back into the anoxic tank. Well, it wasn't quite enough to get the low numbers that they were looking for here. So they still had some nitrate leaving. So they came up with the idea of this anoxic recycle or mixed liquor recycle. So at the end of the aeration tank, remember our goal here is to take NH3 and to make NO2. And remember, this is an oxidative process, and we end up with NO3 with the presence of oxygen. So we have NO3 here, and we pump a whole bunch of that back this direction and back into here. And now we have NO3, we have CBOD. This is the carbon that makes the bacteria want to use the nitrate. And we have the bacteria here in the RAS. And now we have all the ingredients we need to make this anoxic tank work. So hopefully coming off into the atmosphere then is N2 gas. So what happens to the ammonia then that made it through, or that's coming into the treatment plant? What happens to the NH3, or we'll call it TKN? What is actually happening to that is it comes into the plant? Well, the anoxic tank is not aerated. So essentially nothing really happens with respect to the numbers. The ammonification could still be happening, where we're getting some of the organic nitrogen converted into ammonia, which could still be happening, but essentially the number is going to be relatively constant and then flowing into the aeration tank. So the aeration tank is utilized now more for the nitrification process and to polish any BOD that may have made it through the anoxic tank. Now heading into the aeration, or rather from the aeration tank, we could have some NO3 that didn't get pumped back to the anoxic recycle, entering the clarifier. But again, the number is going to be close to the Werman process, where it's going to be close to, say, the 5 milligrams or so of total nitrogen or nitrate leaving the facility. So it's not 100%, effective at reducing it down to say 0 numbers, the total nitrogen, but we do see a large decrease in the amount of ammonia and nitrate and nitrite that has been produced. So we have reduced a lot of that and converted it into nitrogen gas. So it's pretty darn effective. There's a lot of these facilities in the industry. We see a lot of these as the carousel process, like I mentioned a little bit earlier. IMCO, or now Ovivo, I think is famous for the patenting and registration name, the trademark name of carousel. It's a modification of the oxidation ditch, and it uses a pre-anoxic zone to denitrify the mixed liquor. And it's a type of version of the MLE process is essentially what it is. So you see the same kind of layout here where we have the anoxic tank first and then the aerobic tank second. So the flow pattern comes in, the influent comes in here. This is a mixer and it's kind of mixing the tank. And so we have mixing occurring all around here, and the flow comes in here and starts to flow out into the aerobic stage. So the flow comes in and pushes itself through this little gate or channel right here. So we have denitrification occurring here. So we have our nitrogen gas coming off here, and then we go into this basin for the ammonia to nitrite to nitrate processing, and that's occurring here. So we end up down at this end with some nitrate. Now there's usually like a little gate or a little diversion baffle right there, and the mixed liquor either goes back around this way or some of the mixed liquor goes this way. So the mixed liquor has nitrate in it, and so we come back around to the anoxic basin where the nitrate is then denitrified. So there's a little diversion gate right here, or some kind of little channel that allows that mixed liquor to flow back into that basin. So it's called the modified Ludzak-Ettinger process, and it's kind of put into practice here with the IMCO carousel process. Uses the same idea. The outlet gate right here is where the mixed liquor flows over the the gate out of the oxidation ditch into the clarifier, and we hopefully have got most all of the nitrate out, but you may still have just a little bit left going out of the facility. So it's not as much as the influent ammonia that was coming in, around 30 or 40 milligrams coming in. So we've done a pretty good job. Is it 100% effective at reducing it down to 0? No, it probably is not, but it will do a good job. So here's our diversion gate. Some of this mixed liquor is flowing this way. This is MLVSS plus nitrate in it. Some of the nitrate is going out here, and a lot of the mixed liquor is flowing back this way to be recirculated around back to the through the aeration system. So we see a little diversion gate right here, and that goes into the anoxic zone, which is then mixed, and you see the mixed thing occurring here. This is just there's a submersible mixer in here that's getting this all mixed up real good, and we're getting the intimate contact of the raw sewage with the bacteria and the amount of nitrate coming in. So there's mixing occurring, the nitrates coming in, and then being gas is coming off as a gas, as nitrogen gas. So the mixed liquor comes in and then back into the aeration zone on that other channel. All right, so let's say that we wanted to get lower numbers of nitrate or total nitrogen out of the facility. Let's say we want to convert more from the influent total number of nitrogen coming in the plant. Maybe we want to get it down even lower. So the influent comes into this first basin here as the pre-denitrification basin, like we had in the Ludzak-Ettinger process. So if you look at the way this flow pattern is right here, we have the MLE process, but then you also notice that in this case is the kind of go like this. This is the Wurman process, W-U-H, Wurman process. So this is taking advantage of both. So it has pre and post anoxic. So it's kind of a combination setup where we are getting and taking advantage of both of these things. So this might do a little bit better for getting the total nitrate numbers down. And you notice that we have a post-anoxic tank. You may have to feed some carbon right here. So we can't always rely on the endogenous carbon. So we may have an external carbon source being added. Remember, we had different forms of that. And then this number, the nitrate may be much, much lower than before. We might have a very substantial reduction of the total nitrogen into nitrogen gas, and maybe getting our total nitrogen numbers down less than close to 3 or even less than 3 in this case. This is another version of what I just showed you. Now notice that we have the in the four-stage basin, four-stage process, we have the addition here of what's known as a re-aeration tank. So let me back up just 1 second, and you see here we have the dual anoxic zone, sometimes called the A2O process, and we have no re-aeration tank before the clarifier in this one. And in this picture, we have the re-aeration tank in the four-stage part info. So what's the big deal about the re-aeration tank? Well, first off, we're not going from the anoxic tank directly into a clarifier where there will be the potential for more denitrification to take place in that basin, or to go even anaerobic or even septic down in the sludge blankets. So with the addition of the re-aeration tank, we actually get a little bit more oxygen put into place to keep the bacteria from becoming anaerobic. But we also get the agitation of the flux, which then tends to drive off any bound nitrogen gas that was inside the flux themselves. So when we denitrified here, we could actually have flox structure with nitrogen gas bound in it. So when we kind of give this some agitation or a little bit of shaking up of the mixed liquor before the clarifier, we help drive off excessive amounts of nitrogen gas. So the dissolved oxygen or the amount of aeration isn't quite as critical in this re-aeration tank as it is that it just be aerated so that it's getting some dissolved oxygen, but also shaking up that mixed liquor so that we're getting the actual nitrogen gas coming off or out of the flux, which actually it helps the clarifier settle a little bit better. By having those bound gases released, the flux tend to settle better. So it improves the settling in the clarifiers. So the second anoxic phase will generally rely on the endogenous carbon, which is here. The endogenous carbon would be relied on here in the second anoxic phase. However, if you're not denitrifying efficiently, you may have to add a supplemental carbon source, and it helps polish the remaining nitrogen in solution. It helps remove or polish the NO3 to become finally N2 gas, which goes up as a gas. So that's kind of helping polish that. The re-aeration tank helps release bound gases from the flock. Bound gases are going to be gases like nitrogen gas, CO2 as a gas, or even some of the oxygen itself, some excessive amounts of oxygen or just bound air that contains nitrogen and carbon dioxide and oxygen. This helps release those gases so that the sludge settles better. So it aids settling in the clarifiers. It helps add a little bit of dissolved oxygen to the mixed liquor so that the bacteria wouldn't be so prone to going anaerobic or septic in that basin as well. Okay, so here's a couple of questions, and then we'll wrap this up. So the first question says, which conditions described below are most suitable for nitrification? A, higher DO, sufficient alkalinity, aerobic conditions, and a high MCRT. B, anoxic conditions, reduced pH, and a high DO. Letter C, aerobic conditions, short oxic detention time, colder water temperatures. Or letter D, low MLSS, low MCRT, and high FM ratio. Which conditions are most suitable for nitrification? So this answer will be letter A, a higher DO. Remember, we need a little bit more DO than just necessary for BOD removal. We need a higher DO because we got to nitrify. We need enough alkalinity because that's going to be the nitrifier's carbon source and prevent pH problems. We definitely want aerobic conditions. These bacteria are known as aerobes, strict aerobes, and a higher MCRT gives us a higher amount of what we know as MLVSS. So that's also what we need. So that's letter A. So do we have any questions on biological nitrogen removal? I hope I answered a lot of the questions you might have had. Our goal here, again, was to kind of go through the processes as the basic process descriptions. I didn't get too far in the weeds with some of the side reactions and chemical reactions and all. It didn't really serve a purpose for what we want to do here today. We were kind of just giving you kind of an overview, things to look for in the treatment plant that you may experience some problems with, and things you can look for, and also to kind of give you an idea how the process works. So when you're faced with questions on an exam, you'll know how to answer those questions. So that's kind of our goal. I hope that we were able to meet that for you guys. When you're studying for your test, if you still have questions and I wasn't clear on something, or you need a little bit more information, as I mentioned at the beginning of this session, please contact me. And I really do sincerely mean that I'll try to get back with you as soon as I can. My phone number again is 352-294-3881. You can reach me also by email at rtrigar@trio.ufl.edu. And again, my name is Ron Trigar, and I look forward to hearing from you and helping you guys out. And I hope this was helpful. And I'll see you on the next presentation, which is biological phosphorus removal. So see you then. Thanks, everybody.